welcome to TecKXpert webinar on the topic of power quality and harmonics. We will be focusing on the causes, effects, and the remedial solutions. And this topic will be presented by our keynote speaker, Mr. Anil Kumar. The agenda for today's webinar is as follows. We will start with our founder's address, which will be followed by a keynote presentation on the topic of power quality and harmonics by Mr. Anil Kumar. That will be followed by question and answer session and vote of thanks and feedback session. TecKXpert was founded with one vision to organize the world's technology experts onto a single network and to enable sharing of knowledge. Murugeshan sir founded TecKXpert in 2013 with this single vision. So with this vision, we are into the 9th webinar series of TecKXpert Mastermind series. And I would request Murugeshan sir to give the welcome address for the participants to start the session. Murugeshan sir.
Good evening, everyone. It is my privilege to welcome you all in this wonderful evening for the 9th edition of TecKXpert's Mastermind session on Harmonics. Harmonics is found to be the root cause for most of the equipment failures happened in all the industries. Unless otherwise, it is dealt with most care. It will become a killer disease for your equipment, and it is an invisible killer. With request from most of our TecKXpert members to organize a session on this topic, we are here with a wonderful presenter, a subject matter expert in this subject for more than 3 decades. More than 3 decades of experience in power quality and analytics. We are bringing in Mr. Anil Kumar to present this most wanted topic. With this, I request Mr. Shravan to take over further. Thank you all for your support and participation. Thank you, everyone.
Thank you.
Thank you, Murugeshan sir. So with request of the members, like Murugeshan sir rightly said, we have identified one of the best experts available on the topic, and that is Anil Kumar sir. So we now move on to the main topic, that is the keynote presentation on power quality and harmonics, focusing on the causes, effects, and remedial solutions. So a brief introduction of our keynote speaker today. Mr. Anil Kumar comes with a 40 years of rich experience in the field of low voltage and high voltage power systems, power quality, and automation. He started his career at Baba Atomic Research Center as a scientist and later worked for Tata Electric, ASEA, Voltas, and in various middle and senior level capacities at these companies. And his experience in power quality spans across 30 years. He has started since 1990. Maybe that's the time when people actually started talking about power quality. So Anil Kumar was involved in this field right from the beginning of the concept. And he has worked as an entrepreneur in the field of power quality and power electronics, associating with EPRI USA, Gossen Metrowatt Germany, Meres International Finland, specializing in the areas of power quality studies, power system analysis, harmonic modeling and simulation, real-time power quality monitoring, power quality data analytics and solutions, passive harmonic filters, active harmonic filters, hybrid filters, StatComs, SVCs, and energy storage systems. You name the field in the power systems, and Mr. Anil Kumar has worked extensively in that. So with this extensive experience, we are very glad that Anil Kumar accepted to be the keynote speaker for today's event. I will straight away move on to Mr. Anil Kumar to start the keynote presentation. Anil sir, it is all yours. Thank you.
Okay, thank you. Thank you all, and very good afternoon to all of you. I know this is a Saturday afternoon, so I don't know, many of you, of course, these days I know people are working from home. It's normal now, not like the past where everybody is rushing around and nobody has the time. Anyway, I use this opportunity, and I'm sure this will be of help to all of you, because it's about 70 slides, but then some of the slides are just visuals, so that it can give you a quick understanding of the subject. And I'm sure in a time frame of 1 hour, we will be able to finish this. So when it comes to power quality and harmonics, my experience over a period of last 30 years is that for many customers, they look at harmonics and connect harmonics to all power quality problems, which is not so. But then today's program is more to focus on harmonics, so I don't go into the whole paraphernalia of the power quality. But still, power quality is the mother subject of this whole topic. So I will take a few slides on power quality and then move on to harmonics in the subsequent slides. So going on to the next one, for everyone, power quality, to take it as a simple layman's way of expressing, is that you need a sine wave, a perfect sine wave. You should have a magnitude and should have a frequency which is well defined. That means any problem manifested in voltage, current, or frequency deviation that results in failure or misoperation of a customer equipment can be named as a power quality problem. But then that's an ideal scenario, that to have a perfect sine wave. In a normal practical system, you never get a perfect sine wave, which is always going to be influenced by the various network equipments. Like, you have various power electronics, you have various other transformers, capacitor banks, the whole lot of system components, which is not going to make sure your perfect sine wave is all throughout the network. So power quality is fundamentally to look at and see how a perfect sine wave is distorted and what is causing the distortions and how you address those distortions. This is what is the whole concept of power quality is. But going beyond just a general definition of power quality, it is better that we look more in terms of the relevant standards so we get a better understanding of the subject. So let us go to the next slide. The next slide talks about, first you start with characterizing the problem. That is how we can start with understanding power quality. When I say characterizing, there are standards. There are IEEE standards, there are IEC standards, which tries to tell you how to characterize a power quality problem. When you look into power quality, the first standard that will come into the focus is IEEE 1159. In 1159, the power quality is classified as steady state and non-steady state. So when I say steady state power quality problem, it is more to do with this under voltage, over voltage, or the waveform distortions like harmonics, notching, DC offset, the noise signals that runs over the power signal. I mean, we have 50 cycle waveforms. Those are all steady state wave variations. But when you take in non-steady states are those which are not available all throughout the waveform. You will only see it comes and goes like a transient. It just comes and just goes away. A voltage spike just comes and goes away. So those are all classified as non-steady state power quality problems. And harmonics and under voltage, over voltage are all classified as steady state power quality problems. So now everybody must be familiar with this IEEE 519, because when you look into harmonics, that's the common standard followed by everybody. But then what IEEE does is it just looks at the wave shape of the waveform and it tries to see what is the duration of that distortion and what is the magnitude of the distortion. So that means now you can see IEEE 1159 talks about power quality in total, steady state, non-steady state. But IEEE 519 talks on a specific of waveform distortions. Now you look into other aspects of power quality. There is another standard of IEC, that is 61002-5. Here the power quality is understood in terms of frequency spectrum. That means, there is a low frequency, high frequency, and electrostatic discharge. ESD is a separate topic. We don't want to get into that topic now. But when it comes to the low frequency and high frequency, if you look at the low frequency, for example, 50 cycle is your fundamental frequency. You can have frequencies of harmonics, which is 5th, 7th, 11th, 13th, 14th. This all can be classified under low frequencies. That is, it is all below 9 kilohertz. If you take the 50th harmonic is 2500. That's 2.5 kilohertz. That means it's again under the low frequency category. Now, if you go to the higher and higher switching frequencies, then you come across the high frequency category. Now, the high frequency category is substantially electromagnetic interference. It is not, we cannot call it as harmonics. Harmonics at frequencies that is remaining in the low frequency spectrum, say up to 50th cycle or 50th order or the 100th order, that we can say below 9 kilohertz can be treated under harmonics. But above 9 kilohertz, we have to look at noises or electromagnetic signals of higher frequencies. Now, again, when you look into low frequency, high frequency, when a current or a voltage, when it is going through a cable, as the frequency increases, it starts radiating. So that means there is again a radiated interference. So now you can see the power quality is the wider, character of power quality. It starts with steady state, non-steady state, and again it is on the frequency spectrum, low frequency, medium frequency, high frequency. So the whole aspects that influence the performance of a network or an equipment can be called under power quality. And IEEE 1159, IEC 61000, these are all the detailed standards that explains the whole topic of power quality. Now let us go to the next. Now let us look at what is the electromagnetic phenomena when we say. Ultimately, when you say all these power quality disturbances, these are all electromagnetic phenomena. Now, when you look into electromagnetic phenomena, as I said before, depending on the frequency, you can classify as low frequency, high frequency. Now, in the low frequency, again, you can classify as conducted phenomena and radiated phenomena. So now our entire discussion today will be on the conducted electromagnetic phenomena. We don't want to go into radiated phenomena. These are all different topics under power quality. So now let us look at this screen a little more in detail. So what it says, on the left side, it talks about transients, the short duration variation of voltage. And on the right side, it talks about long duration variation of voltage. It talks about voltage unbalance. It talks about waveform distortions, voltage fluctuations, power frequency variations. Now, electromagnetic phenomena, when I say conducted electromagnetic phenomena, under the IEEE 1159 is classified in this table. Now, when you look into how to analyze this, when you say a transient, what is meant by a transient? A transient can be an impulsive transient, it can be an oscillatory transient. And generally, where does an impulsive transient come from? If you get a lightning struck on the line or nearer to the line, you get an impulse, a sudden jerk of voltage transient on the power line. So that is called as impulse. Now, how does that impulse behave? It behaves with a rise time, a drop time, and a peak. That means if you look into that transient on the left side, it talks in terms of the duration, nanoseconds, microseconds, or millisecond. That is, an impulse can remain in a network for a certain amount of duration, and it is also understood in terms of the magnitude. So that means how you characterize a transient is in terms of a magnitude and in terms of a duration. And again, in terms of the rise time, in terms of the drooping time. So this is how a transient is classified. Now, if you look at this, it says a transient is above 50 nanoseconds, between 50 nanoseconds to a millisecond, and above 1 millisecond. Now, if you look into this millisecond story, you know a 50 cycle waveform is a 20 millisecond cycle. Now we are talking a transient, which is sub-cycle or quarter of a cycle. So if you want to capture these sort of transients, you need high-end power quality instrumentation, because you need an extremely high resolution to capture such small variation in your sine wave. Now, the other one which you can categorize is oscillatory. This is another type of a transient. And how does an oscillator transient come from? Now, everybody will be familiar with capacitor bank switching. Now, if you look into a capacitor bank installed in the utility, like in TNEB or KEB or whichever state you come from, the substations, they install capacitor banks. And what is the purpose of the capacitor bank? They install this because to improve the voltage in the network, they bring in this capacitor bank manually. They switch out the capacitor bank so that the network distribution voltage is maintained at the level that is required. Because as the loads are increased in the network, more and more loads are connected on a working day. You will see the load is increasing, the voltage is dropping. You bring in capacitor banks to improve the voltage. Similarly, on a weekend, on a Saturday or a Sunday, you don't need too much of load on the network. So at that time, you don't need a capacitor bank. You switch off the capacitor bank. Now, when a substation does this action of switching in and switching out a capacitor bank, what happens to your power network? The power network will create an oscillation. When I say an oscillation, when you give a sudden jerk to a power network, the network will respond back as an oscillation. This is just like, if you, when the water is flowing, if you suddenly try to stop, there will be a sudden humming or a sudden, sort of a force in the water flow. So a similar scenario you will see in the power network. When you suddenly switch in, suddenly switch out, you will see the network is responding back in terms of oscillations. And so this transient oscillatory transients are one type of power quality phenomena. Here again, if you look into the to the characterization, you have a low frequency, you have a medium frequency, you have a high frequency. That means you can characterize the oscillatory transient in terms of frequency. And number two, in terms of magnitude. And number three, in terms of duration. So you can see all that mentioned in the definition. It is in milliseconds, less than 20 milliseconds, or maybe a little more than 20 milliseconds. That means these are all remains as non-steady state power quality disturbance on the waveform. Now you go into the other area of voltage distortion. Here we call short duration distortions. When you say short duration variation or distortion, it is just could be a sudden spike or a sudden sag in the voltage. So where does the sag in the voltage comes? Imagine there is a short circuit taken place somewhere in the BESCOM network, or let's say a branch of a tree falls over the line. Suddenly there is a temporary short, and when the short circuit takes place, there is a voltage sag. So that sag will be very short period of time, because by the time your circuit breaker will disconnect the fault and maybe the reclosure will reconnect, so you will see that in milliseconds the sag is gone. That means these sags again need not have to last beyond one cycle. One cycle is 20 milliseconds, so it could be below 20 milliseconds. Sag, swells, short interruption, sudden interruption of power suddenly goes and comes back. These all considered as short duration and variation of voltage. Now, when you say long duration variation, this is very common under voltage, over voltages. So that's why many customers use OLTC on a transformer. So when you have a under voltage, over voltage, the OLTC functions and it corrects the system. The OLTC does this because the under voltage, over voltage lasts for a few minutes. So an OLTC as a mechanical device, it can handle the under voltage, over voltages. So whatever I said here, these are all to do with the voltage quality. That means when you draw power from the network, the voltage quality can be influenced by transients, short duration variation, and a long duration variation. Now, when you receive voltage at your receiving end, your load will start producing the current. So the current related distortions are all reflected in waveforms. That means power quality can be defined in terms of voltage quality and current quality. Put together is the power quality. So when it comes to the current related distortions, we will have harmonics, we will have noise signals, we will have DC offset. And then if you look into the other last two parameters, voltage fluctuation, power frequency variation, these are all related to wind farms and solar farms, because these power producing, these are all variable generating source of power. Depending on your sunlight or a wind flow, these generating stations work. So that means their outputs can be variable. So voltage fluctuations and power frequency variations can come on solar farms. So now you can see how the electromagnetic phenomena of power quality is put into a small table like this, which explains the whole aspects of low frequency conducted electromagnetic phenomena. Go to the next. When it comes to power quality problems, there are a couple of factors which causes power quality problems. Certain things could be the utility sources. When I say utility sources, as I said before, a lightning can create an impulse. A substation capacitor bank switching can create an oscillation in the voltage. So those two things are short duration, microseconds or millisecond variations. Similarly, a die bearing plant, a plant next to your building or next to your factory, can also cause the power quality problem. Fault on the network, utility network. In the BESCOM network, if a fault happens on ground fault or a three-phase fault, it can create a voltage sag or a swell. So that also can be an externally generated power quality problems. Tree branches touching power lines, common issue in Bangalore. So these are all insulation failures, because sometimes what happens is an insulator itself on a power line over a period of time can deteriorate, it can fail. and it can create a voltage sag or a swell. So these are all utility related power quality problems. And when you go into the other source of power quality problems are all power electronic devices. I mean, when you look into, if you take a, I know there are a lot of members from the building sector, I would say commercial buildings. If you look into commercial, all these buildings, office buildings or data centers, the amount of power electronics there is, it's almost maybe 50% of your transformer capacity, or maybe more than that. All your LED lighting, your CFL, your variable frequency drives, your UPS, your servers, everything contributes the power quality problem as an internal source. And in a factory, if you go, there'll be a large motor switching on or a switching off. Even an HVAC or air conditioning system, if your large chiller motor is suddenly switches on or a switch off, you will have internally generated over voltages or a spike. Similarly, your capacitor bank switching inside the facility can also cause an internally generated power quality problems. If you go, we look into automotive plants or a steel plant where they have arc furnace or building loads, all those dynamic variable loads also creates power quality problems. So that means sources of power quality problems are at the utility, which is your utility supplier, and also internal source. So that means the PQ problems are caused by the consumer as well as the power provider. That's right. Again, when it comes to power quality problems, we look into this pie chart. This is what is very important is now you can see harmonics. In majority of the cases, your harmonic related power quality problem, when I say harmonic related, a direct harmonic related problem, may not be more than 15 to 20%. But then of course, if your wiring and grounding is not okay, then a lot of problems can happen. A harmonics can get amplified. An equipment can fail. A harmonic can be the cause of the problem, but because your wiring and grounding is not okay, the harmonics can create the failure of an equipment. Similarly, if your wiring and grounding is not okay, then your voltage sag and swell. For example, if a transient or a voltage surge is coming from your power line, and if your neutral grounding is not okay, then what happens on the neutral? You get a transient neutral voltage. That means the wiring and grounding is the basis on which the rest of the system, rest of the factors lies on. But then purely harmonic related problems, if you identify as harmonics related, it may not have to be more than 20%. That means when you look into power quality, you need to look into the totality. When you have to understand when something has gone wrong in the factory or something has failed or something has malfunctioned, then the whole reason from this pie chart can contribute depending on the nature of the PQ problem. Go to the next. Now, I would show this slide. This is the reference standard. So now we can look at it. I mean, when you look into power quality, see the amount of standards that are there. And if you look into the IEEE 519, that's the third standard which is shown in this, is the only one which is relating to harmonics. The rest of the standards are all relating to multiple PQ problems. For example, if you look into the 1159, that is the major PQ standard. It's followed worldwide. So I would say the first three standards, the 1159, 50160 and 519 should be the three governing standard when you look into power quality. Because 1159 talks about voltage quality and current quality. IEEE 519 talks about harmonics, and 50160 talks about the voltage quality of the utility supplier. Now, for example, if you have BESCOM as a power supplier, 50160 governs the voltage quality of BESCOM supply. But you as a consumer, if you are running a power electronic device, then IEEE 519 governs the harmonic standards. 1159 governs all aspects of power quality. Now, there are various other standards, again, which is linking to power quality. And one of the things which I want to talk about, the last one, that is on the IEC 61000 series. 61000 series covers a wide range of individual standards on power quality related emission and immunity of equipment. When I say emission and immunity, for example, every electronic equipment, it can produce harmonics or it can produce electromagnetic interferences. Because if you take even a simple LED or a simple CFL lamp, it produces power. The very function of the power electronics in an LED is that it oscillates. The frequency at which the DC voltage is chopped, and finally, AC is converted to DC by a rectifier, and then DC is converted to AC, required AC voltage frequency. The whole process of conversion and inversion is done at a certain carrier frequency. And that carrier frequency signal adds up to your fundamental frequency and creates a lot of emissions, both in terms of electromagnetic high frequency emissions or harmonic emissions. So 61,000 deals with the emission standards and also the immunity standards. Now, if you have a variable frequency drive, if you have an LED, or if you have a computer, there's an emission standard under IEC 61000. Then also there is another standard in IEC 61000 itself, which says how much that equipment should be designed to be immune to the disturbances. That means emission and immunity are the two aspects covered in the IEC 61000 series standards. Go to the next one. Yeah. Now we come to our subject of harmonics. This is a topic which is going to be given a lot more importance than the rest of the power quality problems which I just covered a little earlier. Now harmonics, everybody will be knowing it is multiples of fundamental frequency. That's the simplest definition you can give for harmonics. If your fundamental frequency is 50 hertz, multiples, odd and even multiples, that is 50, 100, 150, 200, 250. These are all the integer multiples. So that is how harmonics is defined. Now, where does the harmonics can come from? If your load is a linear resistive load or a simple inductive load, there is no need for a harmonics to be talked about there, because a resistive load or a simple inductive load, it can only give a power factor related problem. In a resistive load, you will have voltage and current is at the same, there's no phase angle difference, so you call it in phase. But when it comes to inductive load, yes, there is a power factor issue because there's a lag in the voltage or the current. So now, when you look at a nonlinear load, nonlinear loads are the cause of harmonic problems, because nonlinear load has a VI characteristics which is not linear, like a resistance or an inductor. So go to the next. And as you see, the very way of defining harmonics in a mathematical terminology is you have a square wave in this picture. Now that square wave, if you see, it's a periodic symmetrical wave. So any periodic symmetrical waves can be explained in terms of sine wave and multiples of sine wave. That is what is the whole Fourier transformation that we all learned in our electrical engineering. So now the equation down shows that a square wave can have a fundamental wave of a sine wave, then it can have a third harmonic wave, it can have a fifth harmonic wave. So 1 by 3 is the third harmonic, 1 by 5 is the fifth harmonic. And when I say 1 by 3, 1 by 5, you can also see one is that it has a frequency, that 3 omega, 5 omega all corresponds to the frequency. And 1 by 3, 1 by 5 all corresponds to the magnitude. So you can see this very equation that the fundamental waveform has the full magnitude. And when you go to the higher order frequencies, the magnitude comes down as the frequency goes up. So this is how the very definition in mathematical terms of explaining harmonics. Go to the next. So where do the harmonics come from? As I said before, all power electronics are the culprits of harmonics. Now, when I say power electronics, rectifiers and the inverters are the building block of AC drives. Here it shows AC drive, because an AC drive is nothing but it has a set of diodes at its front end. It takes the AC, it converts to a DC by the diode, and there's a DC bus which holds the voltage with a capacitor, and then that voltage is then inverted to the required voltage and frequency for the motor to run at variable speed. So that means you have a rectifier and an inverter. Both are power electronics. So harmonics, these are all nonlinear loads, so naturally produces harmonics. Go to the next. UPS, everywhere all across, single phase and three phase UPS, again another culprit of harmonics, because here again we do the same principle of conversion, rectification and inversion. And the next one, of course, CFL is your conventional tube light which is shaped into look like a, the old tube light is bent into few small tube lights and put into a holder. That is what this CFL is all about here. And this fluorescent lighting, as you all know, uses magnetic or electronic ballast. Conventional tube lights are all familiar with those magnetic ballast. So these electronic ballast again has a rectifier circuit and inverter circuit, because again this CFL or LED to burn at a constant current, you need to convert that voltage from DC AC to DC and then to the required AC. So there again it produces harmonics. And go into the next one. All your office equipment like computers, printers, fax machines is all single phase electronics, because all these devices has SMPS load, we call it, that is the switch mode power supply. When I say switch mode power supply, it basically tries to convert the AC to a DC and then converts back to the AC so that the device works on that converted AC supply. Again, a source of harmonics. The next one. Now, anything when you go into power quality, the very fundamental approach is characterize it. As I said in the very beginning, IEEE 1159 standard also is trying to characterize the power quality phenomena, whether it's a transient or whether it is a oscillation or it's a harmonics, you need to characterize it. So here, when it comes to characterizing harmonics, how do you do this? Number one is that it will have certain harmonic frequencies, and then it also will have total sum of all those frequencies. So that is how you characterize it. So we go to the slides later, but then when you look into this slide, what you can see is any power electronic device, whether it is a single phase or a three phase, it has certain characteristic harmonics created because the very design of the diodes at the front end of the equipment. When I say front end, the AC power is fed to that device, and when the AC power is coming, you have diodes sitting there. And the diodes does the function of converting the AC to DC. Now in a single phase, you use 4 diodes. If you look at any SMPS supply, you can see 4 diodes in the circuit. And in a 3 phase, you use 6 diodes. So that means you call it in terms of 4 diodes and 6 diodes, but in a variable frequency drive, when you have 6 diodes, we call it as a 6 pulse drive. But in a simple electronic lighting computers, you don't call it like that. You rather call it SMPS based supplies. Now here, when you look into this 4 diode and 6 diode, what you can see from that characteristics harmonic equation tells you the harmonic produced by a power electronic device is related by the simple formula of NP plus minus 1. Now N is any number and P is the pulse number. For example, now let us take the NP plus minus 1 equation to understand a single phase electronic load. As I told you, a single phase electronic load, this is a fax machine or whether this is a lighting or a computer, it has 4 diodes. Now if you put 4 diodes in the P, you put number 4, and then you put the integer 1, you can see 4 plus 1, 4 minus 1. You will see the first harmonic produces third harmonic. So that means NP plus minus 1 is the equation that governs you the characteristic harmonics produced by a single phase or a 3-phase load. Now, based on 4 diodes, you have 3, 5, 7, 9, 13. That is how the sequence goes when you keep changing the N 1, 2, 3, 4. Now go to the 3-phase, and a 3-phase, as I told you, it has 6 diodes. So when you have 6 diodes, you go back to the same equation of harmonic produced by a 6 diode configuration, put N as 1, P as 6, you go to 6 plus minus 1. That means 5th harmonic or 7th harmonic. Now we can see how a 3-phase device creates harmonics. It creates 5, 7, 11, 13 based on the same H equal to NP plus minus 1 equation. So this is how the characteristic harmonics created by a single phase load or a 3-phase load is computed. Go to the next one. Now, this is when you take a switch mode power supply, that is whether it is an LED lighting or whether it's a CFL or it's a computer or whether it's a fax machine, all of them runs on SMPS. So now an SMPS waveform, you can see how it looks like. You inject a perfect sine wave, but unfortunately the SMPS supply changes the shape of the sine wave into like 2 pulses. Now on a time domain, you can see is a varying pulse. which periodically happens in the positive cycle and negative cycle of a sine wave, and it keeps on going on a time domain as long as the load is working. So that is how the shape of the SMPS waveforms looks like, the current waveforms. Go to the next. Again, as I said at the beginning itself, characterizing is what it means, all about how you define the problem. Now, when it comes to the sine wave, which you just saw in a time domain pattern just before in the previous slide, in a frequency domain, if you're trying to convert that, then you will see it has a spectrum of frequencies. The fundamental frequency is number 1. The third harmonic, that is 3 into 50 is 1/50th cycle. The fifth harmonics, 250 cycles. So this is how the typical computer or a typical fax machine or a typical LED's spectrum will look like. It will be predominantly third harmonic and followed by 5th, 7th, 11th, 13th. Go to the next one. Next slide. Okay, now here you have a electronic ballast, which I just said before. The fluorescent CFL uses electronic ballast, which again is an SMPS. It is very similar to the wave shape that you saw in the first slide, 2 pulses on a time domain. As the frequency spectrum of the previous one, that is I showed, the previous one is about a fax machine or a computer. On a CFL also looks more or less the same. It is more of 357. That means in an office environment, you have all those third harmonic predominantly happening because of your lighting systems as well as your office equipments. Now going to the next, the next one is a magnetic ballast. If magnetic ballast has no electronics here, but even in a magnetic ballast, you will have some harmonics coming in. And many times it could be because of the saturation of the ballast itself. You see a third and fifth, a small level of harmonics, because if the little magnetic portion of the, if it gets saturated, then you can have a certain amount of third harmonic flowing. Very small, so I won't categorize this more as a harmonic producing load, but certainly it's a low power factor problem because the magnetic ballasts are all use very low power factor. Go to the next. As I said in the previous one, NP plus minus 1, you can see the same equation here again. You have a 6 pulse drive, which has 6 diodes, and you go back to the equation HPM NP plus minus 1, 6 plus minus 1 is 5th harmonic and 7th harmonic. So if you look into your harmonic spectrum, you can see 5, 7, 11, 13, all characteristic harmonics of a 6 pulse drive. And it also talks about sum of all the harmonics as a TSD graph, because that is how you ultimately try to understand the harmonic indices. When it's a harmonic indices, one is the total harmonic distortion, and second is the individual harmonic distortion. So on a spectrum, on a magnitude versus frequency spectrum, you can see this as a bar graph. Good. And you can also see the current waveforms, as you see the previous one. You can see the current waveform, how it looks like. This is how the current, the chop current, ultimately will reflect back on your power line. If you go and put a harmonic analyzer near to the input of the VFD at the incoming side, you will see a current harmonic which is looking like the second waveform. The first waveform shows the voltage wave shape. I mean, this is how the voltage looks like. Now, you can see the voltage has a small notch on the top. That means every cycle there's a notch, and the notch is coming from the diode switching. That means when you have this 6 pulse diode functioning, by taking the AC and trying to convert to DC, at every time when the diode conduction move from one phase to the other leg of the 6 pulse drive, there is a short circuit taking place. So that short circuit, it is not that you get a complete voltage zero, because ultimately there is a certain amount of inductance and there is a certain amount of impedance which is not going to make sure the voltage falling to zero, but then you get a notch on the wave shape. That is why when you go to a 6 pulse drive, AC drive, you sometimes get a voltage waveform looking like a notch and current waveform looking like those little U shapes. Go to the next. If you go to the 12 pulse, that's another way. I mean, many times people say, I have a 12 pulse drive, so I have no harmonic problem. I don't have to worry about harmonic problem. Yes, to an extent, but 12 pulse drive also causes harmonics which are on the higher order. You can see here 11th harmonic, 13th harmonic, 23rd harmonic, 25th harmonic. And you can also see the voltage waveform has more notching compared to the 6 pulse, where we didn't see so many notches on the voltage waveform. So that means as you go to the 12 pulse drive, VFD, you will see more notches on the voltages, and you see higher frequency harmonics also. Now, this is very important to note, because now, okay, 11th and 13th, it's fine. 11th and 13th is magnitude can be smaller. 23rd and 25, again, fine, magnitude can be smaller. But what happens in a power system is that if you have these sort of resonating frequencies in the network, sometimes these resonances can get amplified by an external transient. It can happen that you have an oscillatory transient in voltage coming into your factory or to your building, traveling from a BESCOM network. And if that frequency matches with your 23rd or 25th frequency, then certainly this can cause catastrophe in the plant. Because I had an incident which I heard from one of my customers for one of the metros. In a metro station, in one of the metros in India, they had a major transient over voltage problem. And where does the transient over voltage came from? Because for them, you cannot have a transient which destroy the equipment. They had a problem of on a 33 kV, they got a transient of about 70 volts, remained for a few cycles, and a couple of equipment got damaged. Those transients can be an extent due to these sort of silent killers. As Mr. Murugesan said before, this can be a silent killer also, because these harmonics, which are not dominant when you connect an analyzer, but you should not neglect it. It is possible that these harmonics can be a killer tomorrow by means of an external transient coming into your plant and resonating at this frequency and increasing the voltage in the network. So you should be careful when you go also into higher frequency, higher pulse drives to reduce the 5th and 7th. Go to the next. Now, to sum up whatever I said before, in the summary of the whole thing, as you can see, there are different wave shapes, the current waveforms, and for each current waveform on a harmonic, on a frequency domain, you can see the frequency spectrum. For example, a VFD produces fundamentally 5th, 7th, 11th, 13th, and a rectifier. I can call it, maybe this could be connected to even any rectification that is done to create a rectifier from AC to DC. You can see the rectifiers created also 5 and 7. All your office equipment, including your computer, fax machine, servers, all that can produce a wave shape like that, which can have a lot of 3rd, 5th, 7th, 9th harmonic. Your LED and fluorescent lighting can cause a lot of 3rd harmonic. Now, if you look at this 3rd harmonic, ultimately what happens with 3rd harmonic? This 3rd harmonic finally flows through your neutral, but everybody knows 3rd harmonic ultimately has a phase sequence which goes in line with the line voltage and line currents. So it is in phase with the line. So that means ultimately when it all comes to the neutral, at the neutral, this is a balanced extra current. That current naturally falls from the neutral. And so the neutral conductor will ultimately carry this 3rd harmonic currents. Go to the next. Now, when it comes to harmonics, I would also touch a little about power factor, because here when it comes to power factor, everybody is familiar with the displacement power factor. Now, for example, if you have a PF meter, power factor meter, the power factor meter will tell you a displacement power factor, which is the cosine of voltage and current. Now, imagine, in a perfect system. Now, here you see, the displacement power factor of a balanced 3-phase network is direct, P by S. That is, divide the active power by the apparent power, and you get the power factor. Go to the next slide. Next slide. Now, here, when the harmonics is in the system, you have a distortion power factor. This is another component of power factor that will reduce the PF or the total system. Now, the distortion power factor is created by all the harmonics that is flowing in the network. √3 UI, that is what is the kVAR. The D stands for reactive power in kVAR. So the reactive power in kVAR, as you all know, the equation is 1.732 into voltage into current. Now here the current when there are harmonics is not just your normal RMS current. It's a sum of all harmonic currents. That's why a distortion KVR is computed based on all the sum of the harmonics. Now when you take that and you bring it into the Pythagoras theorem, you see the total apparent power is a sum of distortion power factor. So when the harmonics is in the system, you can see the power factor goes less than when there is no harmonics. That means the harmonics can bring down your power factor. Go to the next. Okay, now whenever you have power factor problems, natural that you put capacitors in the network. And then what happens? It's a very common thing. When you put a capacitor network, the first thing that happens is the capacitor will absorb the harmonics if it is there in the network, because capacitor is impedance is 1 by 2 pi FC, as you all know. Higher the frequency, lower the impedance, the capacitor will absorb the harmonics. Go to the next. Now, the biggest problem when you put a capacitor network, you can see the single line diagram drawn on the left side. You have a source transformer, you got a capacitor bank, and you got a harmonic source. Now you got a set of another motor, which is the inductive motor. There's no harmonic, no power electronics or no VFD there. But then you have a power electronic device sitting as the third branch of the single line diagram. And now you can see that that is a harmonic producing load. And now when you have a harmonic producing load and when you have a capacitor bank, which is a plain capacitor bank, then what it happens is it can create a parallel resonance. And the parallel resonance, in the simple way of understanding, is that at the point of parallel resonance, your inductive capacity, inductive impedance and capacity impedance becomes equal and opposite. That is how parallel resonance is created. That means the RF, that is the resonant frequency, at the point of resonant frequency, your capacity impedance and inductive impedance become equal and opposite. And in the process, a resonance takes place. That is why whenever you put simple capacitors in your power network, you have to be extremely careful that because these capacitor, instead of improving power factor, it can increase your harmonics. So that is a slide showing. And this increase in harmonics happens due to parallel resonance. Now the next slide. In an equivalent diagram in electrical engineering way, we explain this. If you look at this equivalent circuit, it shows a harmonic producing load. That is a current source. Ultimately, as I told you before, harmonic comes under the current distortion. You connect a voltage, and if the device is nonlinear, it starts drawing a nonlinear current. So it is so always harmonics is considered in terms of a current. It's a current source, harmonic current source. Now here in this equivalent diagram, we are showing a harmonic current source. There is a plain capacitor bank in the system. This capacitor need not have to be a plain capacitor. It can also be the capacitance of your network. Your cables are capacitance. Even all your system both has capacitance and inductive. Even a transformer, interturn capacitance. A cable, the cable from the face to the ground is a capacitance. So the capacitance is the sum of all the capacitance. Need not have to be the standard capacitor that you add for power factor correction. And now the source impedance is your transformer or your rest of the network which is belonging to BESCOM. Now here you can see an equivalent circuit shows the harmonic source on one side, the capacitor on the other side, and the rest of the impedance of the system, including the source impedance of BESCOM on the other side as a parallel network. Go to the next one. So in this parallel network, you can see that when you have a harmonic producing load, how the parallel resonance is created is what is shown in this slide. This AC-DC drive, variable frequency drive, which is basically an a DC rectification and AC inversion. That is why AC-DC is shown like that. And now it is a harmonic source. And now you can see when this harmonic source is producing harmonic currents. Now your entire impedance of the network, the inductive impedance, that is the transformer impedance, the source impedance of your BESCOM network, in parallel with your capacitor bank, your APFC panel, maybe your capacitor bank which is installed in your facility, in parallel when it works, you can see how the equation looks like. The effective impedance of the parallel network becomes zero at the point of resonance. Because when you look into this, it is effective impedance is Z1, Z2 divided by Z1 plus Z2. That is how the effective impedance is calculated. Now, your Z1 and Z2 2 becomes equal and opposite, naturally becomes 0. And that means when it becomes 0, you are dividing by 0, but the voltage can go to infinity, or the impedance can go to infinity. That's what it shows. But in reality, it does not go to infinity, because ultimately impedance has a resistance component and an inductance and a capacitance component. We normally call it R plus JX, L minus XC. This is how we always know impedance is. So we never will have an infinite impedance or an infinite voltage, because in parallel resonance, even though your capacitive impedance and your inductive impedance becomes equalized by each other, the resistance of the network will ensure sufficient dampening is done to control the voltage rise or control the parallel resonance. That is what this parallel resonance is showing. Go to the next one. So now this is again is showing if you put a simple capacitor. I mean, again, it's a very important slide, because normally when you put a capacitor bank to a transformer, here it is showing a 1000 kVA transformer, and you're putting a 400 kVAr, 0.4 MVAr, that is 400 kVAr capacitor. When you put a 400 kVAr capacitor to a 1000 kVA transformer, you will have a resonant frequency at 322 Hertz. That means, if you have an variable frequency drive installed in the plant, or if you have any other power electronics which is producing 5th or 7th harmonic current, you can have a resonance, parallel resonance taking place because of a capacitor sitting in the network, which is 400 kVAr vis-a-vis a 1000 kVA transformer. That means when you add a capacitor to a network, you have to be extremely careful. You should not just think of improving power factor just like that. You should always do whether, when I'm adding the capacitor, does it affect parallel resonance in the network? Where should I install this capacitor bank so that the resonance is avoided? So those aspects have to be looked in whenever you design a capacitor bank in an environment when there are a lot of harmonic producing loads. Go to the next. Now this slide, of course, shows you what it happens when you have a harmonic which is closer to the 7th harmonic. You can see a variable frequency drive is shown here in terms of a 6-pulse drive, and it produces various harmonic currents. This computation of 720, 144 is all done. It's an empirical formula based on which it is calculated. As you know, the rated current, we all know, √3 VLIL cos phi gives you the fundamental current. But then to calculate the 250, 350, 650, you divide by that particular magnitude. As I told you before, in the Fourier transformation, the higher frequency goes by the division of its magnitude. For example, if you want to see the 5th harmonic, 720 divided by the 5, you get into a number which is near to that 144. And so like that, it is the harmonic calculations are done at the respective harmonic current. So here, if you see, when you have a resonance taking place near to the 7th harmonic, you have 103 amps flowing in the network. Go to the next slide. Now this is important. Now this is a very important aspect when it comes to understanding harmonics. As you can see here, your harmonic producing currents, load which is producing harmonics, and then you have a transformer sitting on the top. Now the whole impedance of the transformer and the impedance of the network creates the harmonic voltage. The very fundamental equation that defines the harmonic voltage is governed by this equation. It all goes by the network impedance. Zn is the network impedance. You calculate that network impedance by the percentage impedance of the transformer, the voltage square, and the kV of the transformer. That is how you calculate the network impedance. Go to the next slide. So once you know the network impedance corresponding to the 7th harmonic, and if you know the 7th harmonic current is 103 amps, then you calculate the ohmic value of it, and then you come to the actual percentage. Now you can see, if you go back to the previous slides, you can see that there's a 1000 kVA transformer, and there is a 1000 kVA transformer, and there is a 400 kVA capacitor bank. As you go forward, you will see the 7th harmonic frequency is getting amplified, and you are getting 12.7% harmonic voltage distortion by the 7th harmonic. That means when you add a capacitor in a transformer on a 1000 kVA transformer or a 400 kVA capacitor bank, you are creating a resonant frequency near to the 7th harmonic, and in turn you are creating a voltage, 7th harmonic voltage of 12.7%, which is around 51.5 volt. So this is the way to explain a parallel resonance when you add a capacitor bank into the network. Go to the next one. There is also one more type of resonance called series resonance. I don't want to go into the details of this. Series resonance, if you simply look into it, you can see that the capacitor sitting in your plant is in series with the transformer, which is sitting up, and then the rest of the impedance can create a resonance phenomena in series. When you say series, the entire network impedance and the capacitive impedance can become equal and opposite, and it can also create a very high inrush of current. That is how you can see the rest of the network can send a lot of current. The red line shows the current flowing in at the time of series resonance. That means all your capacitor will get damaged, your transformer will get heated, and your cables will get heated. That means even a series resonance is dangerous if your harmonics producing load. In this photograph, you can also see, you look at the factory on the right side is a factory which does not have any variable frequency drive. This poor guy has only a motor. He does not have a power electronics. He has not purchased a VFD. But look at his neighbor who is sitting on the next side. He's a neighbor. The neighbor has a DC drive in his plant. Now you can see the neighbor is producing harmonics. You are not producing harmonics. And that neighbor's harmonics comes into your factory and creates a series resonance. And many times, sometimes customers, when they want to put capacitor banks in their plant, they think, okay, I don't have any harmonics, so I am going with the plain capacitors. Now you imagine the plight of this capacitor bank. You believe, yes, I have no harmonics, but you are not taken account of the harmonics your neighbor can produce and can come into your factory and destroy your capacitor. So that means, here again, both series and parallel resonance are important when you go for power factor correction. Go to the next slide. Now you can simply see this slide. There's a quick slide. When there is no power factor correction, your waveform looks fine. When there's a power factor correction, it produces harmonics and distorts the waveform. You can see the voltage waveform distorted, the current waveform distorted, because plain capacitors are installed in the network. Go to the next. Now this is again, as I showed you the previous slide, as you increase the KVR on the transformer, you can see the resonant point is getting shifted closer and closer to the low frequency. For a 300 kVR, you can see a 300 kVR resonant frequency somewhere between 7 and 9. The same system, if you take 500 kVR on the same transformer, the resonance is shifted between 5 and 7, and you replace it with a 700 kVR, then you find the resonance is shifted towards the 5th. That means as you increase the size of the capacitor on a transformer, you can see you are shifting the point of resonance closer and closer to 3 or 5 or 7. That means if in your office or in your factory, if you have UPS, if you have VFDs, if you have lighting loads, you are having 3, 5, 7, then you have to ensure that whenever your capacitor bank is installed, you should size the capacitor bank correctly so that it does not cause resonance at lower frequencies. Go to the next. Now, so what we do, the best option is to put a detuned reactor. That is what everybody does when it comes to capacitor bank. So you put a detuned reactor and tune away the frequency from the resonant point. That is what it shows. By putting a detuned reactor, you are trying to avoid the capacitor causing a parallel resonance because you have shifted the resonant point. You should probably, for example, let's say if you put the resonant frequency point at 4.5 or 4.6, it's a non-integer number. So you will not have a VFD producing harmonics of 4.5 order or 4th order. It will only produce a 5th or 7th. So putting a detuned reactor is a way to shift the resonant frequency of the network. Here again, putting a detuned reactor is not a solution ultimately to deal with harmonics. This is only to protect your capacitor bank. The harmonics will be still there. So how to treat the harmonics is a separate subject, but now we are only ensuring that your capacitor banks are protected from harmonics, but the harmonics are still there. Go to the next slide. So this slide shows you how the detuning reactor has to be selected. As you go to higher and higher detuning factor, for example, the most conventional one everybody uses is 7% detuned reactor, that is at 189 Hertz. 189 Hertz is a frequency that lies between the 3rd and the 5th, because the 5th harmonic is 250 and the 3rd is 150, so you are in a safe haven. You put a detuned reactor of 7%, you are keeping the detuning frequency between the 3rd and 5th, and so there is no amplification of harmonics. Similarly, put a 14% means you are putting the detuning below the 150. You are putting the detuning number between the 100 and 150. That means again, you are not amplifying a third harmonic current or a fifth harmonic current when you put a 14%. So that means in majority of office buildings and banks and data centers where you have a lot of third harmonic, it is always safer to install 14% detuned reactor so that you're detuning the circuit far away from the third harmonic frequency. Go to the next. Again, the same one, detuning. It is just you're detuning. When you put a 500 kV, you're detuned, a capacitor bank, you detune it, you're shifting the frequency between third and fifth and trying to protect the capacitor bank. That is what is detuned to avoid resonance, it says. Yeah, go to the next. And now to just sum up harmonics, what all harmonics can cause, it can cause neutral overloading. As I told you, third harmonic current can flow through the neutral always because it is a zero sequence current. When it's a zero sequence current, any balanced network, you will not have negative and positive sequence currents in a balanced network. When an unbalance comes, certainly a harmonics causes an unbalance, and then you have a positive, negative, and zero sequence currents. And the zero sequence currents are the current that rotates in line with the positive sequence current. So that means it comes to the neutral and flow through the neutral. That is why the neutral is getting overheated. Your transformer gets heated because of harmonics, because the issue of harmonics is that one is your transformer no load losses increases because of all the hysteresis losses, eddy current losses, all these losses are proportional to the square of the frequency. Then also harmonics increases due to skin effect. It increases the resistance of the cable. So that means your I2R loss goes up. That means the harmonics, the impact of harmonics can be increases in all the losses across the network. Your transformer, your cable, everything get overheated. Breaker tripping, naturally, as I said before, if there is some phenomena happens by a non-steady state resonance, it can end up in a tripping of a breaker. Or it could be, tripping can be due to any other non-steady state phenomena, as I explained the power quality itself. Your capacitor banks will get stressed out because naturally capacitor bank gets overstressed because it is a 1 by 2 pi FC is the equation. So higher the harmonics, lower the impedance, higher the overloading. So that means you're stressing the capacitor a lot if you don't correctly design the capacitor bank in the environment of harmonics. The voltage distortions, and when you say, as I showed you before, the notching or when you have higher order harmonics, what happens is your voltage waveform shape will change. Your perfect sine wave oscillates at 20 milliseconds. That means it has 3 zero crossover points. Now if you imagine multiple frequencies will have multiple zero crossover points. Now if you have a time clock which is working on the perfect sine wave, the clock can misbehave or your controller can misbehave because your zero crossover happens multiple times on a 20 millisecond frequency wave. So that is what is this zero crossover is meant. These are all again mentioned as noise because noise is a phenomena, as I told you, it's a higher frequency or a low frequency phenomena which is above the harmonic frequencies that can be created by your LEDs or your VFDs. All this produces noise signals, and these noise signals passes over your power frequency waves, and it creates again so much of disturbance waves on a fundamental wave. With a high-end analyzer, you can always capture and see how a noise looks like on a power frequency waveform. Go to the next. Your motor heating is another major issue. When I say motor heating, I would just say that because when you take a harmonic current, when you take a fifth harmonic or a seventh harmonic current, the fifth harmonic current is considered as a negative sequence current. And the fifth harmonic current, as you see, number 5 stands for a frequency which is rotating at the speed of 250 cycles. Now, if you have a harmonic current in the motor stator winding, you can imagine the magnetic flux inside the motor will start rotating at 350 cycles. This is again a negative sequence current. That means when you look at the rotor side, the rotor will be injected at 6 times the fundamental frequency will be the magnetic flux the rotor will come across. That means what happens on the rotor? This negative sequence current can create a reverse torque on the rotor, and the bearing can fail sometimes. The motor can overheat, the motor can fail. So that means one of the impact of overheating of induction motors due to harmonics is because of these negative sequence currents. Go to the next one. Yeah, that is again the fifth harmonic current. Okay, typical problems created. You can, as I said, the tripping of the breaker, the fuses, blowing of fuses, keep going. And then you have your, as I said again, the higher I2R losses, higher when you say higher losses, you can see the next picture. something is burning out, this is your motor or your breaker or your transformer burning out. These are all the problems of harmonics. As I said before, the skin effect problem, the higher the harmonics, higher the resistance. Because if you take a cable, when you inject a 50 cycle current, you can see the middle picture. It has an AC resistance which is reduced, and as you go further and further, I don't say AC resistance reduce, even the area of current flow is reduced. You take a harmonic current, you will see the area of current flow reduces to a very small peripheral area. That means your effective resistance is going to increase because your resistance is rho into L by A, and if the area comes down, your R goes up. That means higher the harmonics, higher the resistance, higher the resistance, higher the losses, I squared R losses. Go to the next. Yes, this is again, as I said before, how it flows through the neutral. Go to the next. As I said before, the capacitor fails because of harmonics, because 1 by 2 pi FC. Next, how capacitor failure will look like. Ultimately, I'm sure many of you would have seen such thing in real scenario, not in a photograph. The next. Now you can see this. See, when you have harmonics in the network, you see how the RMS current increases. With a 44% distortion in harmonic current, 44%, you will see the RMS current is going up by 10%. That means now you can see your RMS current, your cables, your equipments, which are all rated for a certain amount of current, you have to look into derating, because you have seen that when the harmonics is in the network, you have 10% increase due to that harmonic currents. That means derating is what is, what is specific in this case. Go to the next. When it comes to IEEE 519, yes, there are stipulation in terms of what is the harmonic permitted in low voltage. The total harmonic voltage distortion is 8%. Individually is 5% for low voltage. As you go to the higher voltages, you have reduced distortions. Go to the next. Here it talks in terms of current harmonics. The current harmonics goes by the fault level of the network. But again, in the IEEE, we go by the TDD, not the THD, because THD is an instantaneous value. TDD is computed based on the full load current. THD is calculated based on the instantaneous fundamental current. So the IEEE, if you want to implement a harmonic study according to IEEE norms, you need to look at these tables and very carefully make sure that it complies to it in terms of TDD. You don't have to worry about THD. You have to look into TDD. Go to the next. There are other IEC standards, which is very important, especially when you have all office buildings and commercial buildings. You have a lot of LEDs and your VFDs. The IEC has well-defined standards, says what should be the harmonic produced by a device which is less than 16 amps. For example, when you use a VF, a LED, or when you use a computer, you can go by IEC 61003-2. You can say to the manufacturer, yes, the harmonic emission limit for the computer or LED I will buy from you should satisfy 3-2. Similarly, 3-4 says above 16 amps, greater than 75 amps. So these standards defines in terms of what is the permissible harmonics emission by various devices. Go to the next. There are variable solutions for harmonics. I'll get on to this. There are a couple of solutions. One is to install a line reactor for the VFD itself. You can go to the next slide. As you can see here, you have a variable frequency drive, which is shown by a diode and an inverter, and there is a motor. And by installing line reactor, you can see L2, that's a line reactor. You can reduce the harmonic currents produced by the VFD because a reactor works always as an opposing force on higher frequency, because as you know, inductance is 2 pi FL. So higher the harmonics, higher the impedance. So the reason why you put reactors at the input of a drive is to reduce the effect of harmonics. Go to the next. As you can see in this, as you install different type of line reactors, you can see when you put a 2-person line reactor, you can see how the harmonic comes down. For example, if you put a 2-person line reactor, you can see if fifth harmonic is somewhere between around 50%, your seventh harmonic is somewhere around 30%. Now, let us say if you put a 3-person reactor, you can see if you put a 3-person reactor, you can bring down your fifth harmonic. If you can see your fifth harmonic graph. You put a 3% in the middle of this, between 2 and 4, you can see your fifth harmonic can bring down to somewhere about 40%. That means when you put a line reactor at the input of the drive, you are ensuring the harmonics injected by the drive is reduced depending on the size of the line reactor. But then you cannot go and put a 5% line reactor or a 6% line reactor just for reducing the harmonic, because ultimately the line reactor causes a voltage drop. And finally, if your VFD has to run a motor, you cannot put a big line reactor. Sometimes it will affect the speed torque characteristics of the drive and all that. So you should carefully select the input line reactors. Going to the next slide. This is, it's called a passive filter. You go to the next, I can explain that a little better. In a passive filter, when you put a passive filter at the input of the drive, here we are showing a waveform of a current which has about 39.9% harmonics at the input of the drive. Now, by putting a passive filter, the passive filter is a LC filter. You go to the next slide, you can see how it looks. You put a passive filter at the input of the drive. You can see again a VFD, input side rectifiers, output side inverters. And if you put a passive filter, these passive filters are like a broadband harmonic filter. And what it does is, the harmonics produced by your drive is completely removed at the output of the drive by installing. So this is one of the, for example, your HVAC applications. You have your large drive used for chillers and all that. You can put this passive filter and reduce the cost of putting an active harmonic filter and reduce the harmonic impact. So this is the concept of passive filters. Go to the next slide. When you put a passive filter, you can see how the current distortion comes down from the previous slide. It has come to around 4.6%. I was showing the previous slide around 30%. So you can see the shape of the current also. See, you can see the current waveform with 39.9% harmonic distortion. And as you put a passive filter, you can see the current is in a perfect shape. It's about 4.6%. And the next one is, this is active filters are the subject we are going to talk here. There is again, I think this active filter, there was one or two slide was missing. Okay, fine. The active filters, let us go to the next one to explain about active filters. Yeah, I think that one slide was got overlapped. See, I just want to, before we go to the active filter, the previous slide was a little misplaced. The other way of filtering the harmonics is using tuned passive filters. As you can see here, if you have in a network, you have like in an office situation or in a factory, you have lighting loads, you have variable frequency loads, then you have a lot of third harmonic, fifth harmonic, seventh harmonic. Now in this particular example, we are showing you have fifth and seventh. You can install passive filter to tune it away. So this is another way. As I said in the previous slide, either you put a passive broadband filter at the output of the drive and remove the entire harmonics coming out of the drive, or you put a passive filter at the main LV switchboard and filter the total harmonics in the network. But the passive filter solution has its own plus and minus. So I won't say putting a passive filter is the best solution. Whenever you have to go for passive filter, you have to always properly design and decide what is the right solution and where you should install a passive filter. Go to the next one. Yeah, this is a passive filter is showing. Go to the next. See now coming to the active filter. Now active filters are called as the very advantage of active filter is that it can filter the harmonics without any function like a passive filter where you remove 3, 5, 7. Here you can remove the entire harmonics as a broadband filter, or you can remove selectively the harmonics. So the advantage of active harmonic filter is a very simpler device in terms of filtering harmonics. It's easy to install. It is just a shunt device. Unlike the previous slide I was showing you for a VFD, you put a filter at the terminal of the VFD. That's a series device. That means you have to break the cable. In a shunt device, you put an LV panel, take one of the outgoing breaker, and the breaker you can connect it to the active filter. That is how you connect a filter. Go to the slides. Yeah. Now, an active filter is in principle, it is just like a VFD. Yeah, more like a VFD, I would say, because a VFD also got rectifiers, IGBT. So here also, it also has the same thing, but in a different topology it is done. An active filter fundamentally has an IGBT drive, and we call it a voltage source inverter. For the fundamental of understanding voltage source inverter is that it has a DC source, that is a battery, and the power electronics converts the DC voltage to the required AC voltages. So in an active filter, it is trying to create harmonic currents at multiple harmonic frequencies. So the IGBT bridge is doing that function. Go to the next slide. So now you can see here, you have a load at the right side. You have a CT's input coming to the active filter. The active filter has an IGBT switched technology, and the active filter is switched in and switched out at a particular frequency, depending on the frequency to be compensated in the network. Now, if you want to select all the frequencies from the second harmonic to the 50th harmonic, you select the filter as a broadband filter. The switching will take place and remove the harmonics which is between the second and the 50th. Now you can also select it as a selective filter. Now if you say I want to remove only 5, 7, 11, 13, you can select individually and program the filter, and the filter will automatically take out all that. So it's a far simpler concept when it comes to mitigating harmonics. So, and again, as you see here, the IGBT technology also, this concept is called a two-level topology. That is, it has 6 IGBTs. The latest active filters have 12 IGBTs. We call it 3-level topology. A 3-level topology has a lot of advantage on a 2-level active filter, because in terms of noises, in terms of life, in terms of the losses, in terms of the size, and in terms of the overall cost of ownership, you can bring down the total cost of an active filter by going from 2-level topology to the 3-level topology. When I said 2-level to 3-level, the only difference is in 2-level you have 6 IGBTs. In 3-level topology, you use 12 IGBTs. And by doing that, you are going to reduce the stress on each IGBT, because every IGBT is doing the function of cutting the voltage at a particular frequency and creating the harmonic currents. Now, if you put 12 IGBTs instead of 6, you are reducing the stress on each IGBT. That means the life of the IGBT will be extended, the life of the active filter will be extended. Go to the next. Active filter, what it basically does is, this is again very important to know. So sometimes people say active filters just creates an anti-harmonic current and it just injects into the network. That's a very layman concept, I will say, so widely talked about. Active filters are fundamentally a low source impedance device. When there's a low source impedance device, the active filter produces harmonic currents as a low source impedance. That means you put a VFD load, and the VFD load will see a low source impedance, that is the active filter, instead of taking the harmonic current from a high source impedance, which is a network. Now, if you put a transformer with the rest of the network, the source impedance of the network is much higher. You put an active filter in parallel, that has a much low source impedance, and it creates, so the load will always try to go to the active filter, which is a low source impedance, and take the harmonic currents from there instead of taking the harmonics from the network. So that means active filter produces harmonics as a low source impedance device. That's a most electrical engineering way of explaining an active filter. Now you can see active filter, this IS is the source current, that is the current which is flowing in from the transformer, and the IL is the load current, which is the load which is connected to the transformer, and IF is the filter current. Now you can see IS is the source current from the transformer is reduced to the extent of IF. IS is IL minus IF. That is the equation. That means the source current is reduced. That is how an active filter will protect the transformer from absorbing harmonic currents from the network. Go to the next. Now, this is when you take the source current, it has two aspects. This is the IAF. Sorry, IAF is the active filter current. Active filter current you can split into 2 parts: harmonic frequency currents and reactive current. So IH square, IR square, square root of that. Go to the next. It explains a bit. So now what it shows is, if you have a 300 ampere active harmonic filter, it can, and if you have a harmonic current of 220 amps, that means this active harmonic filter can give you 220 ampere of harmonic current, and it can also give you 204 amps of reactive current. That means this active harmonic filter with 204 ampere reactive current, you can use it for power factor correction. That is how active harmonic filter does the double function of power factor correction and harmonic filtration. So if you correctly size the active harmonic filter, sometimes you may not need a capacitor bank. The active harmonic filter itself can give you For example, a 204 will be, if you multiply by 1.732 into zero point 0.4, it could be somewhere about 100 plus kVAR. That means this can give you around 130, 140 kVAR of reactive power compensation and 220 ampere of harmonic mitigation. So a properly selected active harmonic filter is more than enough instead of going for a capacitor bank. Go to the next. And now some warning, these are all the last slides, where the active, when you say an active, it is very important, it's applied for a successful application. You have to be very careful in terms of how you select this active harmonic filter. So what it says, where the active, how it is applied is very crucial. You have to that means it should be done by careful study. You should not just blindly buy an active harmonic filter and just install it. And the active filters are very low source impedance. So this is a very important point here, because sometimes people put active harmonic filter in a network, and if your variable frequency drives don't have any line reactors, then what happens here? Your active harmonic filter, being a low source impedance, will inject more harmonic currents. So that means when you select an active harmonic filter, you need to make sure that the drives have proper line reactors. Otherwise, there's an additional current of 20 to 30% more will be demanded from the active harmonic filter. And sometimes the active harmonic filter can get overloaded because of this reason. So 20 to 30% more current downstream. Okay, go to the next. So that means, yeah, therefore an active harmonic filter should be connected as near, because again, where to install an active harmonic filter? Sometimes it is important, it's always good to put an active harmonic filter near to the source of the problem. If you have a lot of VFDs downstream in the network, it is better you put an active harmonic filter near to those VFDs rather than putting an active harmonic filter at the main LV panel. When you go and put it at the main NV panel, the problems are, number one is it increases the size of the filter, because you need to take care of a lot of other factors. And number two, as I said before, it's a low source impedance. So when it says a low source impedance, it injects a lot of harmonic currents will start flowing. So in the process, downstream your main LV panel, your harmonic distortion will still remain high, even though your harmonic distortion is low at the main LV panel. So that means it is better to put an active harmonic filter near to the source of the problem. And also capacitor bank, when you're putting a capacitor bank, make sure the capacitor banks are detuned. If your capacitor banks are not detuned, then there is a question of resonance, because active harmonic filters also produce harmonics, and there can be a possibility of resonance by the capacitors in the network. Without detuned reactors, you should not put capacitors. Similarly, your drive systems, you should always ensure that there is a 3% line reactor at the input of the drive, so that the harmonic overloading does not take place for the active filter. The next one is, yes, I think the next one. You go to, I think the remaining slides are far simpler. And now, a quick one run on this, because there are some other VFDs. It can come with front-end active rectifiers. That is, we call it active front-end drives. The issue with active front-end drives, it's a good concept. The active front-end drives can reduce the harmonics, but at the same time, it will increases the electromagnetic, interference in the network, because an IGBT sitting at the front end of the drive produces high frequency currents in the network. So you will have issues with regard to a lot of noises coming from the active front end drives when you put it that. So you have to make sure that proper electromagnetic interference compliance is done before we put such active front end drives. And active front, go to the next slide. The active front end drive, as you can see here, yes, the harmonic, it shows an example of ITSD 8.8, and so yeah, it shows how the active front-end harmonic reduces the harmonics. Go to the next. But at the same time, this is a very important slide. You can see here, when an active front-end drive is put, you have harmonic frequencies at 3361. That 3361 relate to more than 3,500, which relate to more than 7th harmonic. So that means you have 3,600 harmonic frequency currents will flow in the network. That you have higher frequency harmonic currents generated by active harmonic current. So you can see here, near the 5th harmonic, that is at 3 kilohertz. Yeah, you can see between 3 kilohertz and the 10 kilohertz. So you can see here, this comes with 3.3 kilohertz is the high frequency current generated with the active front end drive. That means whenever you go for this low harmonic drive, it also produces higher order harmonics. So that is again is dangerous to the network. As I told you in the beginning, it can sometimes cause transient over voltages. Go to the next slide. Active front-end drive, okay, you can see how the voltage looks like. It carries a lot of noises. That is why the voltage waveform looks with a lot of small ripples on the top. These are all high frequency current that is coming from the active front-end drive. And sometimes these noises can cause problems to electronics. So you have to, and if the grounding is not proper, sometimes these noises can pass through the ground and come to your electronic cards and increase the DC voltage there, and the electronics can fail. So this is how the active front-end drives creates problem for sensitive electronic devices. Go to the next. Yeah, active front-end drive, okay, it is lower efficient, it is, when it comes to between active harmonic filter or when it comes to active front-end drive, I would certainly say active front-end drive, you see, it has the efficiency is somewhere about 93%. If for an active filter, it's about 95%. But if you go for a passive broadband filter, it's 97%. That means, so whether you have to go for an active front-end drive, or whether you have to go for an active filter, or whether you want to go for a high-pass filter for a VFD, has to be decided based on these engineering aspects. You put a high-pass filter, it gives you much higher efficiency. It has its own benefits. But if you have an active front-end drive, it has its benefits, its own demerits. Active filter has its plus and minus. So ultimately, your right engineering means you have to select the right choice. And reliability factor is a question in active front-end drives because of the it's a lot of electronics. So sometimes possibility of service, cost of service, replacement of cards, and it produces electromagnetic interference. So all those issues. Active front-end drives are more complex. Again, active front-end drives can sometimes cause issues with the generator because of the high frequency harmonics. Generator has higher frequency. Generator always have a high source impedance, so you can increase the harmonic voltage distortions, and which is again create instability on the generator. Go to the next. Interaction with the standard AC drive. There is significant evidence from around the world that active front-end drives can force the DC voltage. It can increase the DC voltage. That these are some of the issues with active front-end drive. So my discussions are now to compare the technologies. So I will not spend too much of time on this. But then one good point I should say about active front-end drives is it can also be a regen drive, that we can regenerate. Active front-end drives can send back the extra energy that is available in a rotating motor back to the system. Sometimes, active front-end drives can be also used as a regeneration drive. For energy efficiency concept, active front-end drives give some energy advantage. So you have to look at the trade-off between all these concepts. Yes, I think, Next. So it is harmonics, if excessive, it can be harmful to your plant, your equipment, your production, and the life of, okay, it's a safety issue. It can also be, if it is managed well, it can be very cost effectively handled. Retrofits are possible, but sometimes can be more costly. So you need to see what is the right way of mitigating it. No form of mitigation is perfect. So you need to have the right experienced people to look in and advise you how to go for mitigation options. And VFDs are a group of harmonic polluting products. So make sure proper line reactors are used so that the active filters can effectively work. Go to the next. Again, active front-end, active filters, if you can look into all, you can three-phase and four-wire systems. So three-phase, three-wire system, three-phase, four-wire system, all these sort of applications are possible with active harmonic filters. So you need to select, which type of filter you need to buy. If you want to go for three-phase, four-wire, if you have a lot of non-linear loads of lighting loads and all that, you should select a four-wire system than a three-phase, three-wire system. And then also wherever you also should do proper measurements where you measure the harmonics and install any mitigation is crucial. Don't select and install filters without proper harmonic studies. The mitigation should be installed as near as possible to the harmonic producing load, as I said before. The next slide. Yeah, that's it. It's a long one. I know I was trying to compress as much as I can and trying to speed up as much as I can. I hope I could convey the message. Thank you for your attention, and thank you all. I will now see any questions.
Thank you, sir. I think that was a highly insightful presentation. I think we truly understand the meaning of you are a doctor of power quality. That's how simply I can put it. Now I
Thank you.
open the room for question and answers. I think you can use the raise hand option to ask your question. I can see a few hands raised. I will request Mr. Gokul to go ahead and ask the question. Gokul. Mr. Gokul. Okay, moving on to Mr. Mahendra.
Session with lots of learning. I have just only one simple question that I do have PF correction unit in my plant. However, I get leading power factor penalty.
Okay.
And I was observed using power meter, even after switching off the APFC panel, then also my power factor shows in leading on the power analyzer. So what could be the reason?
I see why you have a lot of leading power factor even when you switch off the capacitor bank is fundamentally your load power factor is leading itself. That means with how the load power factor goes leading is because when you have a lot of non-linear electronic loads like lighting loads, UPS loads, BFD loads, or any other power electronic loads, all these loads are highly capacitive in nature. That means these loads produces leading power factor by its own natural choice. Now, if you put capacitor bank, the capacitor banks are only going to cause more leading when you add extra capacitor banks in a system which is already on a leading power factor. So the answer to such problems are like, I would ideally say an active harmonic filter is the right choice. And when I say an active harmonic filter, the active harmonic filter can be selected to compensate the leading and lagging power factor on a real-time basis. When I say on a real-time basis, that means cycle to cycle, it looks at when is the leading taking place in a cycle, when is the lagging taking place in a cycle, and every cycle it injects the leading or lagging reactive energy and keeps the power factor near unity all the time. So the answer to the question is to go in for an active harmonic filter with the option to give leading and lagging reactive energy along with harmonic mitigation.
Sure. Thank you.
Thank you very much.
My pleasure, sir. Thank you. Thank you.
Thank you. So moving on to Mr. Gokul. Are you there?
Hello.
Yeah, Mr. Gokul, go ahead.
Hello.
Yes, Mr. Gokul, go ahead.
Please.
Sir, actually, in our company, we had faced many fire accidents regarding this. So we introduced the reactor in the lighting system. After introducing the reactor in the lighting system, the amount of fire accidents has reduced. So how this reactors are calculated, sir? On what basis?
Now the thing is, you said the reactors in the lighting system. I couldn't.
It looks like an inductive reactor only.
No, but what I'm saying is, your what type of lighting system you have? Your all LEDs and
all LEDs, all LEDs.
And where did you put the reactors?
Into the input side, sir.
Of the you are talking about of the LEDs?
Yes.
Of the LED. See what happens is, but what about you have capacitor banks also with you, or there's no problem with the capacitor?
We have the capacitor banks also, even then it happened.
But my question was your capacitor banks. You have any problems you have faced with capacitor banks?
Yes, sir. Actually, some of the capacitor banks also blasted.
See, now here you have two problems. See, one is that your LEDs. What happens with the LEDs is LEDs are it basically converts the AC to DC, and then later on it converts to the AC because LED has a driver. LED that driver is a SMPS load, and this driver is switching at a frequency of sometimes in the range of about 60 to 80 kilohertz is the frequency at which the driver keep switching, that LED driver.
Okay, sir.
When I say LED driver, LED has an SMPS circuit and it has a switching frequency because that switching frequency is in such a wide range, and that switching frequency current is coming back to your 50 cycle current and creating these problems. So now when you put a reactor, what happens is the reactor is trying to oppose the change of current. So I would rather say if you have proper LED with the right EMI filtering, because LEDs produces higher frequency noises and higher frequency and harmonics. So proper EMI filtering along with LED, there are LED manufacturers who provide this also as a part of the LED, the driver itself, that the electronic driver card, it comes with an EMI also. You have to see whether it has EMI filtering option in that.
Okay, sir.
Now, what you have done temporarily putting reactor, you are trying to, sort of reduce the impact of those high frequency current. What a reactor does, reactor is 2 pi FL. Higher the frequency, higher the impedance. So you are trying to, but the reactor will create overheating. So that means, you put reactor, but it creates overheating and it can cause some other problem. So I think when you go in for these LEDs, you have to make sure the LEDs have proper EMI compliance. That is why I said before, go into IEC 61000-3-2 compliance standards and make sure that LED, when you buy it, it satisfies the emission standards. That means it does not produce EMI and harmonics beyond what the standard says, so that you don't have this problem. And coming back to the capacitor bank failures, certainly I'm sure there are certain harmonic amplification happening, as I said before, parallel resonance problems. So that could be the reason for capacitor failures. So the quick answer is yes, go in for LEDs with EMI filtering and capacitor banks correctly designed so that it does not get amplified. Your reactor is a temporary solution because it is opposing the rate of change of high frequency currents coming from the LED. So it is saving the system now.
Okay, sir. Sir, actually, we are on some 600 to 700 LEDs. Okay, it's all 4 feet LEDs. So this EMI filters, we need, it is available in the drivers, right, sir?
Yeah, see, that is what, see, this sort of failure should not happen if you ask me. Now, the best thing is to do a study and see this, because I would rather say by connecting analysis, we can capture the actual waveform, and then give a correct recommendation, because I'm quite sure this is a very, very solvable problem, and it is happening because of the high frequency switching taking place in the LED. And put an analyzer, capture the waveform, and put a right solution. That's the right approach.
Sure, sir. Thank you, sir.
Yeah, thank you.
Thank you. Thank you, sir. Moving on to Mahadev Swami, sir.
Sir, good evening. Thank you, sir. Your complete information is very useful to us.
Thank you. Thank you.
Yes, sir. Sir, I have a question that this ACF filters installing at variable frequency output near the load is better than it means. When we go to the customer, they will be in terms of money. I don't have much money in my pocket. Only I have this one. You give a solution. I should not have any penalty from the government. How much it is expensive? Is it 30% more than the main input it is connecting? When we are going for a solution at individual VFD level, sir?
See, now putting at individual level a passive broadband filter is expensive. I will never recommend that. Putting passive filter all across at the drive input is an expensive choice. The best solution is to put line reactors at the VFD inputs. You have to see whether what happens with VFDs is sometimes VFD comes with a DC choke. Okay. Sometimes the VFD comes with the input line reactor. An input line reactor of 3% can bring down the harmonics to the tune of around 30%. And here, all these things, the right approach is to analyze the problem at site. If you have multiple VFDs running parallel, then also harmonic comes down, because multiple free VFDs diverge, because every VFD has a particular firing angle of when it switches on, switches off at a particular firing angle. So all the VFDs will not work at the same firing angle. When the firing angle varies from VFD to VFD, the impact of harmonic also comes down. So I would rather say in this particular case, or if you are proposing such solutions, yes, cost is an important thing, but to economize the cost, do a good system engineering and decide whether line reactor is the better option, or a common active filter is the better option, or a common passive filter. You can put together these VFDs. For example, let's say you have 10 VFDs of 50 kilowatt. All the 10 more drives of 50 kilowatt, then you put together 500 kilowatt as total, put one passive filter for all the 500. So that way also you can reduce the cost. That means you have to do that engineering and optimize the cost. That is how we can bring down the cost, I would say.
Okay, sir. This line reactors at VFD drive input, will it affect the DG operation when the power changeover from EB to KEB to generator voltage regulator, will it affect because of this?
So this line reactor will not have any impact on that, because the line reactor is just sitting there to reduce the harmonics coming out of the VFD, and it reduces the harmonics. In one way, it is good that the generator will not get subjected to that level of harmonics coming from a drive. So I would rather say a line reactor is a good solution, and it is rather helpful for the generator.
Okay, okay. Sir, by installing this active harmonic filters, is there energy saving in overall? Because that active harmonic filter itself will consume some power. So if energy saving is there any return on investment calculated? Any case study if you have?
Yes, I would rather say one is okay. The case, how it saves energy is, for example, it's all now. If you in a given plant or a building, we have to first see how much is the power factor there, how much is the harmonic produced in the network, and how much can be the wattage losses in the network from the line through the connected devices, through the transformer up to the main source. So that means this is computable. The wattage loss in the network can be always computed. When I say wattage loss, if you have high harmonics, your transformer losses goes up, your line losses goes up. If you have a low power factor, your reactive energy current goes up. So again, the losses goes up. So I would say that yes, return on investment calculations are possible for a given system if we have a lot of harmonics, and if the plant is at least, I would say, a plant of a size which is having somewhere about 1000 kVA transformer. On a 1000 kVA transformer, putting a 100 ampere or a 200 ampere active harmonic filter, we can easily work out a return on investment. It's not a problem. But if you go to smaller and smaller, then the energy efficiency, energy saving may not happen much. But above 1000, 2000 kVA transformer, you will start seeing much higher energy saving and better return on investment. And again, coming to the active harmonic filter, as I said before, there are different topologies in active harmonic filter. If you go with an active harmonic filter with a higher loss, for example, there are active harmonic filter which is having losses to the tune of about 4%. If you go with 3-level topology, the loss comes down below 1%. So that means that 3% losses on the active harmonic filter also energy loss. So, so that means better technology active harmonic filter, and see how much is the harmonic level in the network, see what is the power factor in the network, what is the size of the network, what is the wattage losses in the network, and then you can calculate the return on investment. It is possible, I would say. And if you some, based on a typical case, now for example, your own case, if you can just say this is a single line diagram, then we can give you an ROI calculation for
that. Okay, thank you, sir. Thank you.
Moving on to Mr. Ayavaru.
Yeah.
Go ahead, sir.
Very good evening, sir.
Good evening.
Yeah, thank you very much, sir. Anil Kumar Garu, it's a very nice, wonderful session. I have a small doubt. Is there any, like ground alone, how much total harmonic distortion it can reduce? This is my small one doubt. Second doubt also.
Can you repeat that question? I couldn't.
Suppose in the electrical network, ground alone, how much total harmonic distortion it can reduce in the THD?
In an electrical network, in terms of, but you have a lot of harmonics in the network.
Yeah. Is there any specific calculations for that? Ground alone in the electrical network.
You are talking on the grounding part?
Yeah.
On the grounding side.
Ground, we have any electrical network, definitely we have ground system, right?
Yes.
So ground alone, suppose even though in spite of having all reactors, capacitor, bank, irrespective of all these filters, ground alone, how much it can reduce in the total harmonic distortion?
Very good. Good question, sir. In fact, that is why in a couple of earlier, in the beginning slides, I was telling about what are all the various power quality problems one can encounter in a facility. The harmonics can be many times a cause, but sometimes the cause need not have to be reflected as harmonics, because if you have a little amount of harmonics in the network, let's say you have a 20 ampere or a 50 ampere harmonic current in a 1000 ampere network, it's very small. 50 ampere is nothing to worry about. But the problem is this 50 ampere fellow can cause a catastrophe later. Now coming back to your grounding, what happens is when your grounding is the way to protect the equipment as well as protect the people, not out. Now, many times when you have harmonics produced by all these harmonic producing loads like AC drives, LEDs, AC drives can be kept away for the time being. The LEDs and other single phase electronic loads produce a lot of third harmonic current. So the third harmonic current naturally flow through the neutral, and it can go into the ground also, depending on how the capacitance between the neutral to the ground. We call it like, those are all the noises. You can have, so if the grounding is not proper, certainly the impact on the ground will be such that the harmonics flowing on the neutral or the harmonics flowing on the phase.
Other phases,
That is one part. Second part is the higher frequency current that flows in the phase and in the neutral through the capacitive and inductive impedance can reflect on the ground system. And then it can create a ground current and a ground voltage. Now, if your sensitive electronics fails due to this ground voltage, then the answer lies there. Depends on what is the sensitivity of that electronics, how important is that electronic device, in the system. So coming back to this question, physically, to say, okay, we can always compute and say what is the extent of impact on the grounding in a given network due to harmonics and higher frequency current. We can compute and tell you this is the impact. The financial saving, of course, the only thing is, okay, you have to then improve the grounding and reduce it. I mean, so the cost of that, or sometimes the cost can be very high because you need to look at whether there are, implication in terms of your bearing failures and all that. Yes, the answer to that question is yes, we can determine what is the impact on the ground and accordingly tell you what is the improvement you need to do on the grounding. That we can recommend you.
Oh,
thank you.
Right, sir. So at least 1% or 2%, something like that, can we calculate? No?
Not
exactly calculation, it's based on experience, at least I can say.
Certainly, it is not just 1%. It can be even more, and it can be even it can be a catastrophe which is waiting. See, I have come across some just quickly. There are some hospital scenario I have come across where the hospital has a lot of electronic card failures. And the electronic card failures, one of the fundamental reasons for the electronic card failure, as I understood, was the grounding was not okay. So all the electronics, one is 2 to 3% saving in one aspect, but the second aspect is a couple of lakhs of electronic cards in the hospital, patient's life. All that.
In fact, crores of equipments will be there in the hospital, biomedical equipment. True. Correct.
Yes. So this, I would say it's certainly 2-3% is a very small number to say. It impact can be much larger in a larger network.
Well, good, sir. Thank you. One more small I can have. Time is there for me? One more question.
Yeah, please.
And is there any government rules for harmonics, like PF has to maintain certain end user? Do you have any proposal, or is there any rules, such a rules in our Indian government?
The power factor regulation, according to the Central Electricity CEA Act, true. CEA has come out with the regulation saying that the PF should be plus minus 0.95.
True.
This is the CEA regulation, is plus minus 0.95. That means if you can go to leading also 0.95, but lagging should not be below 0.95. True. Leading should not be, but then the utility, state electricity boards have their own ways of, so that is where the problem is. Now in Maharashtra, it is very particular, the reactive energy, leading and lagging are all penalized.
Yes.
Karnataka, I don't think any penalty is there.
I'm asking once again, is there any such a rules for the harmonics?
On the harmonics also, see, again, CEA regulation is very clear that IEEE 519 should be followed for harmonic regulation. See, CEA has come out with all this regulation last year. And they are sent it to all these state electricity states to implement this. So it's a matter of time that this will come, and the implementation will be harmonic voltage should not go more than 8% at the coupling point, and harmonic current should not go more than 8 to 10% to 15% depending on the fault level at the point of coupling. And the power factor should be within 0.95 plus minus. So this is already there. Maybe it will come as a law in the coming times, I think.
Well, thank you.
Sir, do you have any documentation regarding this CEA circulation, sir?
Yeah, yeah, it is there. CA regulation, this document is there.
Okay, please.
Yeah, I can send it to our team. I think our friends can send it to you, not a problem.
Yeah, please. Thank you.
Yeah.
Moving on to Mr. Suresh.
Hello, good evening.
Good evening, Mr.
Can I audible?
Yes, please go ahead.
Yeah, sir, it's a very nice explanation on this topic.
Oh, thank you.
So, one doubt is now the industries, they are going for online solar projects, this small project without net metering.
Yeah.
My question is, this solar project, which can generate any harmonics? If yes, which type and how we can mitigate that issue? With active or either passive filter?
Actually, the solar, it all depends on the inverter design again. Generally, what I find in the solar, is this a rooftop something or is it a
rooftop?
What would be the size of the solar plant?
We installed 10 kW and other 20 kW. So near about 3% or 4% of the entire load.
Okay. See, certainly, if you ask me, there will be harmonic currents will be there, but then we have to, filtering harmonics of such small projects can be very expensive. So one has to really look into the actual situation. For example, if you have capacitor banks and all that, I would have rather suggested instead of putting capacitor bank, you should have put a small active harmonic filter, which could have taken care of mitigation of harmonics as well as power factor correction. Now, I would rather say these sort of solar plants, the right option can be install this sort of active harmonic filters, which will mitigate harmonics and maintain power factor near unity, so that the kilowatt hour consumption from the solar plant can be optimized also. Otherwise, the solar plant has to pump in reactive power, which is not what it is meant for. So I would say, yes, harmonics problems as well as power factor problems will be there. But the investments has to be looked into, because smaller plants, it cannot happen that, you see, minimum harmonic filter size will be around 50 amps. And the minimum 50 amp harmonic filter, which can combine power factor correction and harmonic mitigation, can cost you somewhere about 7-8 lakhs. So you have to decide, this is the equipment price, and then the connection installation can add up the cost further. So you need to look at it. So my answer here is, yes and no. Harmonics, if it is not causing a problem, you need not have to worry. But I would rather say, do a simple measurement and keep a record with you. That is important.
Currently, we are getting unity power factor, but we have plan in next to go for a more solar power rooftop. So I won't worry about that in future, because I am reducing the power from the MSDSL and we are generating more solar power. So that is any impact of harmonics or something like that. So that I want to understand. Actually.
Yeah. See, I would rather say, if you are thinking of adding a rooftop of a size more than 100 kilowatt and all that, I would certainly say that you have to, instead of going for capacitor banks and all that, you should actually go in for active harmonic filter as a part of the package itself. So it gives the phenomenal benefits in terms of the overall cost of investment. But smaller capacity, we have to go by case to case. But I would certainly say that any solar plant installation, one of the simplest thing you can probably do is to have a power quality meter to record this continuously. Every solar plant, you can put a PQ meter and record this. And at any given time, over a period of 1 month, 2 months, if you find that there is some problems that happened in the place, then, you can attribute whether it is harmonics or not. But I would certainly say, I have not come across in a solar plant, anything is failing just because of harmonics. If grounding is not okay, sometimes you can have electronic card failures and all that. But again, the total system design is how I look at the whole thing. I cannot just look at only from a harmonic perspective here.
Sure, I think. Thank you.
Thank you.
Moving on to Mr. Satyanarayana.
Yes, sir. Hello?
Yes,
yes,
please.
Yes.
Sir, is audible?
Yes, please.
Yeah.
Sir, first, thanks for this session, sir, Mr. Murugesan, sir. And excellent harmonic session from Anil Kumar, sir.
Thank you.
Thank you. Sir, our problem is that we have a 6.6 megawatt solar power plant. We have connected to the grid through a 33 kV cable. The length of the cable is 9.7 kilometers. For the maintaining of the substation and the lighting, we have taken 70 kVA CMD, sir. But every month we are getting 400 kVA bill. That means the CMD is getting raised 3 times. But while seeing the load on that area, it is near about only lighting load is there. Just 2 to 3 motors are there and lighting load is there. We are not able to understand why that CMD is getting raised to 400 kVA load, sir.
What is the power factor there? What is the power factor?
We are maintaining 9.95, sir. Power factor is 0.95.
Because I don't know whether you are not getting penalized on leading power factor and all that in this case, is it? No leading.
No,
power
sir.
factor.
No. We don't have any penalization for leading and lagging power factors in Telangana. But we are penalizing for the higher CMD.
But here, when you are generating, what is the capacity of the solar plant you said? It's
6.6 megawatt.
So you are generating 6.6 megawatt at its peak on a daytime, no?
Yes.
But then when you are generating 6.6 megawatt, whatever, okay, that much a kilowatt hour you are sending to the grid, and then you are doing banking or something with the customer, or how do you?
It is net banking with the government, and we are utilizing for the 2 campuses. One is for I'm working in Infosys, Hyderabad. We have 2 campuses in. One is at Pocharam and one is at Gachibowli.
Okay.
We have a what it is called utilization, that is at some percentage at Pocharam and some percentage at Gachibowli. We are doing like that only.
See, what I would suggest is, we need to let us record it for at least for a week at this point.
Sir.
And see, when I say a week, generally, okay, these electricity bills, when they give on a monthly basis, it takes monthly average and all that. But a week, we have to actually plot the graphs, how the kVA graph is, how the power factor graph is, how the kilowatt. And so once you see these graphs, and we can also plot the waveforms with the graph. So we need to, I think a proper measurement can solve this problem, I can tell you. Because today, when I sitting at distance, when we are discussing like this, I'm quite sure that kVA going up means certainly it is not that there could be some period of time, because this again they go by the computation of peak happening on a 15 minutes computation or something like that. No, they go by that maximum demand. That's how they calculate. No, there's a window. So that means what I would suggest is to get rid of this penalty. Once we do measurement, we can see which load at that peak time can be avoided, so that, you don't get this penalty. That can be done. A measurement and the solution can be easily done for this problem, I'm telling you.
Okay, sir. Okay, sir. Thank you. Thank you very much, sir. Thank you.
Moving on to Mr. Rajapandian.
Sir, good afternoon.
Good afternoon.
Hello.
Yeah, good afternoon. Thank you.
Thank you for knowledge in the harmonic study. Then I have one question, sir. But I have 350 kVA APC panel with T-tuned reactor. Particularly 100 kVA reactor, 2 times it is a white phase lead only burnout. So what is the reason? Any harmonics is there? But there is no loose connection. Nothing is happened, but the same phase lead only burn out like a welding. This lead is fully cutted. So what is the reason, sir?
See, there are 2 things. One, of course, is one is when that particular step on only you have this problem. You have said that you have a 350 kVA. You said you have a 350 kVA capacitor bank.
Yes, the total panel, but failure is 100 kVA unit only.
How many 100 kVA steps you have?
Only 100 kVA, 250. But 100 kVA Q-tuned reactor white is only burn out.
So all the steps are with detuned reactors, no?
Yes.
Your reactors on all the steps.
Yes.
Okay. No, I see there are 2 reasons. One is that, as I was telling in the presentation, whenever you have harmonic current in the system, the RMS current also gets affected. That means if you have a reactor, the reactor rating, every reactor 100 amp, it will be rated for 100 kVR will be rated accordingly. For example, at 25 kVR is rated. If you want to rate for harmonics, it should be somewhere about 40, 42 amps, it should be rated. though your normal current will be 32 amps, when it comes to RMS current, that means the reactor current rating can be one aspect. Whether the reactor is getting overheated and the problem is happening, number one. Number two, yes, when this particular switching is happening, whether there is some harmonic resonance is taking place. So either the RMS current is more than what the reactor can handle, or the resonance is the two reasons for this problem. So I will say that, but when you run it by disconnecting those 100 and run it with only some less than 250, are you having any problem? If you just disconnect it and keep running that other steps alone. Hello? Hello?
Mr. Raja, are you there? Looks like there's some technical glitch. So
yeah.
maybe you can continue with that answer, sir, assuming.
Yeah. No. So my point here is that, one thing you can do is that, you can check whether the rated current of the reactor on the nameplate detail, you can take and check that. And that is one aspect. And second aspect is see what are all the variable frequency drives, other non-linear loads if they are in the plant. That is the second aspect. And we have to see whether these non-linear loads are causing any resonance. And the third is where this capacitor bank is installed in the plant. So see, these are all basically a plant study, and looking at the problem can easily give a solution. I'm sure it is either due to a resonance problem or due to the sizing problem. Because however it can be, see, when a 100 kVA step, when you're trying to switch in, the amount of inrush current also will be very high. So perhaps if you put an analyzer and check the effect of switching currents at multiple steps, we can easily find out whether there is any switching over current or switching over voltage coming at that point of time causing this problem. So that means the answer is put an analyzer and check.
Sure. So we need more data to understand what is the exact reason.
Yeah, we can easily find out this, because these are all by measuring we can find out the problem.
Thank you, sir. Moving on, Chandresh.
Good evening, Mr. Anil.
Good evening. Good evening.
A wonderful session.
Thank you very much, sir. Thank you.
Now I have a question. Are there no problems happening on even harmonics, especially in the chemical industries, where I have come across even harmonic resonance? So is there a solution for those type of problems?
Yeah. See, when you go for an active harmonic filter, the active harmonic filter is can filter even harmonics, integer harmonics, non-integer, interharmonics, everything. For example, when you say where does even harmonics come? See, normally if you have a perfect rectification of a sine wave, as I was saying in the beginning of the slide, in a UPS or a VFD or a LED or a CFL, all these places, the rectification is a full wave rectification and a perfect matching of the positive side and the negative side of the waveform, symmetrical waveforms. Now, even harmonic comes when the symmetry is gone. Now, why fundamentally even harmonics can come? The VFDs or the electronics, if it's a firing angle is not synchronized or the firing angle is not working according to the design, certainly it produces even harm, because then the rectification is not symmetric periodic waveforms. The rectification will be non-symmetric. So it contains even harmonics. Sometimes it can also contain non-integer harmonics. That means instead of the second harmonics, you can have a 2.5 harmonics also. Now, active harmonic filter is a solution to avoid all such problems, because that's the only solution for this, because active harmonic filter can filter second to the 50th harmonic in one go.
Not all active harmonic filter do even harmonic.
No, that's what you have to. You rightly said that. That is what you have to go with the right manufacturers. And there are active harmonic filters. See, again, what happens is some of these active manufacturers I know want to only put selective filtering, because the moment it goes to broadband filtering, the active harmonic filter efficiency comes down. Number one. Number two, the active harmonic filter derating issue comes up. That means should be properly derated, which again, everywhere economizing the cost, so we don't derate. And the third thing is active harmonic filter produces higher frequency harmonic currents. So sometimes these high frequency harmonic currents need not have to be within the harmonic range. It can be in the 900, 9 kilohertz, 10 kilohertz, and then those 9-10 kilohertz produces electromagnetic interference as noises. Then through ground, your electronics can fail. So that's what the right actual harmonic filter is very important. Otherwise, all these cumulative problems can come.
Okay. How dangerous is this even harmonics?
See, any level of harmonics in a network is a silent bomb. It is, as I was seeing, there was an incident, as I know, in a metro, where the 30 kV voltage has gone to 70 kV as a transient over voltage. And when they did the analysis, they found that the network was resonating at a frequency which was at a higher order, like, in the beyond this 30th and 50th harmonic order. And then whenever there's an externally injected oscillatory current comes in, this gets amplified. So that means you have to ensure that if there are harmonics in the system, measure and find out what is the level of harmonics in the system. And if it is something which is alarming, filter it out. If it is, if you find that, okay, the harmonics are there, but I still want a lock option, then try to redesign, shift the capacitor bank, shift the load here and there, and remeasure and see whether the harmonic has come down. But always, putting impedance in the network, even if it's a second harmonic or whatever harmonic it is, even harmonic, if you have some reactance in the network, that harmonic will be removed out at the source itself. So, because ultimately reactance will try to oppose the rate of change. So this can be, don't leave it as it is, mitigate it either by reactor, either by filter, or shifting the equipment. You need to have some solution. Don't leave it as a problem. It will, a non-steady state power quality problem can sometimes sort of, trigger this silent one to a big wave.
Okay.
And can cause a tsunami at that time,
Okay. Okay. Yeah. Thank you, Mr. Anil.
My pleasure. Thank you.
Okay. Mr. Gopal.
Good evening. Thanks, TecKXpert, and thanks, Mr. Anil, for such a wonderful
session. My pleasure, sir.
Yeah. My question is, we have installed a 250 kVAR bank in one of our facility with a 12-stage relay. And the lower segment is like a 5 kVAR, 10 kVAR, 15 kVAR is only switching on because we have to just adjust only small factor of the power factor. But the problem what you are facing is frequently the contacts are getting burned. So what might be the reason?
Yeah, the straight answer can be, one is it could be switching currents. When you have multiple small steps, does it have reactors or a simple capacitor?
Yes, it has the reactor, 7%.
7% reactors also. The contact will be failing only because the two reasons. One is the switching current and the switching voltage.
Okay.
Because when you switch in and switch out a capacitor, certainly it creates a high switching current or high switching over voltages. So the contactor is the switching device which is handling that problem. So that could be the reason. But see, again, even if when you are whenever you have capacitor banks in a harmonic environment, and if you face any problems like this, measure it is the right way. Because when you measure it, you will exactly know, because these analyzers these days comes with waveform recording and all that. It is not like the conventional harmonic analyzer. It can record the waveforms. When it records the waveforms, it exactly captures the waveform and show the waveform itself if there's a switching over voltage there. Then you can even probably put a small MOV or a small surge arrestor and make sure that that switching over voltage is removed from the system. So I would rather say measure it, but then this problem is straight because of the switching currents. Because when you have multiple capacitors getting switched on, also more switching currents will come in, and it is not that one capacitor alone. Maybe one capacitor switched on and the next capacitor switched on means the previous capacitor also will inject current into the next capacitor. So that means the contactor is going to be facing more switching currents, But these contactors have resistors also in parallel?
Yes, yes.
Even the resistors also, these days, that is, I think we should measure and see how the waveform looks like. Okay. And then the solution can be very easy then. We can even catch the manufacturer of the contactor and tell them, say, look, you are said this is the resistance you have provided and the switching current is only so much. And now is the resistance or the contactor is failing.
Okay.
With the proof we can fight.
In case if you are suggesting a surge arrestor, do we need to place it for each unit?
Yeah, you should. But I would suggest, and even putting a surge here in each step, if you are to put surge arresters to avoid the surges coming from. But then the major issue will be that this is the placing the surge arrestor. Maybe you have to put some MOV. You have to look into that. But then I would rather say why don't you measure it and then take a call? No, that will be ideal.
Okay.
Then we can see by looking at what is the level of the voltage, the transient over voltage. Sometimes what happens is some of the suppliers can tell you, okay, put a surge arrestor there. So it's one solution. But sometimes the peak of the voltage is such that the surge arrestor may not see the peak. The surge arrestor will still sit there. It won't clamp the voltage. It will sit still there. And the surge arrestor will fail over a period of time because every time it is getting subjected to a peak, which is not actually more than the switching, it's smaller than that, So deterioration of surge arrestor can happen if you wrongly select it also.
Okay. Okay, thank you.
Thank you.
Thank you, sir. Moving on to Mr. Chidambaram.
Yeah, good afternoon, sir.
Good afternoon.
It was a wonderful session, basically.
Oh,
We learned a lot. Yeah, I'm basically from the hotel industry. I'm working as chief engineer. Yeah, actually, we have a it's a group called Accor Hotels, and we have a lot of hotels. And every year we used to take care of a lot of audits in terms of safety. And so, do you suggest us that the harmonic test will is mandatory to have a kind of a safety audit in a year or something like this? Will it be helpful?
It will be. See, this is not just as a harmonic audit; it's a power quality audit.
Yes.
See, what happens is that in a hotel scenario, the couple of aspects. One is that how much wattage loss is happening across the network, because your reactive current, active current, and harmonic current, all the three currents increases the wattage loss in the network. And some critical areas, these wattage losses can be so high that it can deteriorate the insulation over a period of time, and it can cause fire and those issues. So I would certainly say that power quality audit is required. And I would also suggest that, see, my experience, over a period of time, I have seen people going with the power quality analyzer and just connected the main LV panel and then give a report. I think for a hotel scenario like this, one has to look at the overall safety requirement of the hotel and the electrical system in terms of electrical safety, and then determine which are all the points where this measurement has to be done, and what is the data we should actually look for. That means there should be a proper method statement, a proper objective, and the location, which are all the location. Then you will find this is becoming a very good information for the safety of the system. Under a simple measurement, I would say it is not going to fetch any results.
Yeah. That's true. That's true. Thank you so much, sir. Thank you so much.
Thank you. Moving on to Mr. Kasiraman. I think last two questions.
Good evening. Good evening. Good evening, sir.
Good evening.
Thanks to Mr. Murugesan and Mr. Sharvan. Sir, Anil sir, it was a really wonderful and insightful session. We learned a lot.
Thank you.
And I have a basic doubt, sir. Sir, we have a 6.6 kV, 18 MVA AFE drive. It is driving a 12 megawatt motor.
Okay.
So when we switch on the drive, the harmonic content is going beyond the 50th order as well.
Yeah, that is what.
We ordered this drive to some X company. Parallelly, while ordering for the passive filter, we have gone with the Y company due to management decision on the commercial part. Unfortunately, end of the day, the filter did not give the desired results. How should I approach this issue, sir?
Now, here you have two problems here. One is the harmonics problem. Second is the electromagnetic interference problem.
Exactly.
Because so now here the thing here is active front-end drives have the IGBTs at the front. So naturally, these IGBTs are switching at a higher frequency, maybe 16 kilowatts or 80, whatever is the designed level for which it is designed for. Now, as the switching frequency of the IGBT is increased, certainly your wave shape will become better, but it will carry a lot of, the higher electromagnetic interference waves. So I would say that we should measure this EMI and the harmonic impact with the without the filter, and then with the filter. And by looking at the waveforms, we have to see whether we can do some readjustments or redesign of the filter, because this whoever has supplied you that EMC or that passive filter, I'm sure that they probably can have that data and redesign that and make it work for you.
Yes, sir. Yes, sir. Actually, when we ordered, we do not have much knowledge on this, the level of harmonics which is going to be generated by the drive and all, and we could not interact properly. After at a later date, yes, we came to know that after a lot of study and all, the filters to be tuned properly to mitigate the harmonics and all. And after that, we got some information from the drive manufacturer, and then shared. And there is a dispute. So thank you, sir. Your input noted, sir. I will get back to you through Murugesan, sir. I take your number and then call you, sir.
Yeah, please. Yeah, thank you.
Thank you, Kasiraman sir. Moving on to Mr. Karthik.
Yeah, hi. Good evening, Anil sir and entire TecKXpert team.
Good
It was a great session. I'm actually a non-electrical guy. I'm just into product and sales management, and my interest to learn more about a product before I sell it to my clients is what drove me into this TecKXpert group.
Okay.
So this power quality thing, I just had one query. Since last 2-3 years, we have been seeing a couple of leading OEMs approaching clients with a new solution rather than along with a capacitor and a reactor which is detuned with aluminum or copper, depending on the voltage needed. They're also suggesting a thyristor-based switching module solution.
Yeah.
So, is there any threshold you would suggest, like for example, for a load for an industry which is having more than 2 MVA or 10 MVA or 12 MVA loads, they can go for thyristor-based solution, or is there any scenario wherein it is really needed?
Yeah. See, generally what happens is between a thyristor switching and a contactor switching, the only difference is the speed of switching. How fast the switching of capacitor is done. That is what is decided by thyristor vis-a-vis a contactor, because a thyristor can switch in a couple of milliseconds. For example, about 40 milliseconds or 60 milliseconds. That means when I say 40 millisecond or the 60 millisecond, in the electrical terminology, it takes 3 sine waves to pass through. Now, if you go for a contactor switching, it can take over a second. So that means contactor is much slow in responding to the power factor correction than a thyristor. Now you have to look at the load. Is your load is dynamic and fast changing? If a load is changing very, very fast, then only you need very fast correction. If the load is more or less steady, how do you know whether the load is fast or slow? Is by connecting an analyzer and take the load pattern, see how the current is varying over a period of 24 hours, how the power factor is varying over a period of 24 hours. And if you find that these variations are not extremely fast, then contactor switching is more than enough. Selecting thyristor switching is, you need to do a bit more detailing. I would certainly say that that is not the thing, go for thyristor switching. One has to see whether thyristor switching is really going to improve the average power factor and whether it is really needed for the load, if the load is fluctuating fast. For example, a welding load. Welding is a highly fluctuating load. There thyristor switching makes sense. But if you go and put for a compressor thyristor switching, it doesn't make any sense, because that does not, once it is at a given speed, it will just run at that speed. It does not keep changing the load. So there a contactor is enough, that's the answer.
Yeah, understood, sir. Thank you very much, sir.
Thank you. So I think that's concluding of the session, sir. I would request.
I have 2 questions, Shravan.
Yeah, Murugesh, please go ahead.
Okay, see, there were about 6 questions. Out of 6, 4 were already answered. So one is, will capacitor burst in UPS could be because of harmonics?
Capacitor bursting in UPS, because how it happens is when your AC input is, power is coming from the AC input to the rectifier or the UPS, and there is a DC bus thereafter. This failure can be many times an voltage quality problem. So one has to, is it just happen once in a while issue, or is happening frequently?
This was received through mail, sir.
No, what I'm saying, UPS DC side capacitor failure, I would relate it to a couple of factors. One is the quality of voltage. If there is a voltage sag or a voltage swell that I presented at the beginning, the short duration voltage variation, a sag or a swell can impact the DC bus or the capacitor, the UPS. For example, when a voltage sag takes place, there is a lot of interest current. That capacitor can fail under that interest current. If there's an voltage spike, the DC bus voltage goes up and it can fail the capacitor. So we have to see, is it happening, whether the quality of voltage received at the UPS side is good. That is the first step we have to see. Harmonics by itself cannot cause a problem just like that. Harmonics can be a problem, as I said, if the grounding is not okay and all that, then sometimes through the grounding effect it can happen. But then quality has to be measured at the input of the UPS. If it is a regular problem, it's easy. Otherwise, you need a little longer duration measurement. And then we can solve this problem, I can tell you.
Okay, so a study has to be recommended, right?
Yeah, because you need to look at the voltage quality. You look at the harmonics, but you should also see the voltage quality.
Okay, sir. Thank you. And one more question is, sometimes we are hearing some vibration noise kind of thing in our raising main bus bar. Is it because of harmonics?
And see, the thing is that again, it can be sometimes noise also. It depends on what is the type of load you are feeding through the bus riser. And if it is a mechanical vibration, we should see whether it is due to an electromagnetic, field created that is creating an electromechanical vibration. So I would certainly suggest that if you have a load data and, then measure it. And then we can see whether there are noise in the signals which is causing, an undue mechanical force due to the, the noise in the bus bar. The noise.
So again, a study is recommended, right?
Absolutely. See, any electrical engineering is such that it is everything is invisible to us. We see we only see the physical phenomena, but without the mathematics and the measurement, we'll never know what is causing the phenomena.
Absolutely. Yeah. This end of the session, Shravan, you can go ahead.
Thank you, sir. Thank you. So we move on to a vote of thanks. I would request Ravindranath sir to do the honors, please. Thank you.
Am I audible?
Yes, sir. Please go ahead.
Sir, Anil Kumar sir, we are extremely grateful to you. We as TecKXperts, we have been blessed to listen to you. This subject, what you spoke non-stop for nearly 2.5 hours, if we start say 3 to 5:30, more than the subject you delivered, the energy level, the passion with which you conducted the session, the interest with which you answered, it is really mind-boggling, sir. Your level of knowledge and then your interest to disseminate whatever you over the years, hard working of so many years, accumulated wealth of knowledge you came forward to share with the TecKXpert group. And many of us have been a silent beneficiary of your experience and a wealth of knowledge. So we are very, very grateful to you. And then this, I would say, for TecKXpert group, for us, we represent, for you, Mr. Anil Kumar sir, I should tell you, we represent, are you a TecKXpert member? I'm not sure.
No, I'm not.
Okay, but that is why I thought I should mention this to you. We, the TecKXpert group members present in many countries, we are all representing many different sectors, hospitality and facilities, IT-enabled services, manufacturing, infrastructure, and many such sectors people come from. And then getting to listen to a specialist like you, and then this subject being for an electrical engineer, for which this group has now no dearth of, this is an extremely specialized subject. And very few people come forward to learn this, and very few come forward to share that what they learned. And you being a thorough professional, we should consider ourselves extremely lucky day today to listen to you. And we learned a lot, and more than what we actually learned and carry with us today, it is generating more questions because you have done your job, because you generated more questions in your mind. How to avail, when to take a power measurement, what are the criteria, what is the base parameter that should be considered before calling for a power quality, harmonics study in particular. So a lot of fog in the mind has been cleared. Your non-stop reference. Many of us, I mean, it's too complex for us to grasp everything what you presented, but it benefited all of us in certain way so that we can apply it in our workplace.
Thank you.
And the impact of your knowledge definitely it make many of us to look at this subject in our workplace and engage in a post quality study, and then call the right people to engage the services for whatever the problems that you face. So thank you very much, sir. We're extremely thankful to you.
My pleasure. Thank you very much.
Sir, Mr. Murugesan, sir, I should tell you that your dedication, sincerity, and the passion with which you've been conducting this webinar ever since this lockdown started in India, it is unparalleled, unmatched, sir. I don't know what energy level you have, what motivation you have. Every week you come out with a subject and you get hold of a topmost expert in the domain and make us all benefited. And then it is very, very highly devoted on your part to conduct these sessions. Very thankful to you, Mr. Murugesan.
Thank you, sir. Thank you. And now I would like to add here, everybody's contribution is here, sir. Everybody is contributing, of course.
Yeah, thank you, sir. I hope that before, even after the lockdown gets lifted up, this webinar will continue. And definitely, Mr. Shravan Gupta, you're great. You made the session actually so interesting with your moderation. We will ever remain indebted to you for whatever you're doing. Thank you, Shravan.
Thank you.
Thank you, sir. All the credit goes to our fantastic speaker today. Thank you, sir. I think with that, we'll move on to Murugesan, sir, for closing comments, and we can proceed further. Conclude the meeting. Thank you. Murugesan, sir.
Good evening all again. And today's session was fantastic. Anil sir, you nailed it. Actually, see, this was one of the subjects which we do not know, and most of the people are neglecting. But now, after your webinar, and this will be taken care, and I'm sure that each and every industries they will do something on this, and they will take care of these issues in a much better way. And the understanding what you have given is phenomenal. Thank you very much, and thank you all participants.